Right now, as you listen to this, Earth is surrounded by forces that almost no one notices. Invisible magnetic currents are flowing through the space around us, stretching from the Sun out past the orbit of Pluto and beyond. These fields are restless, twisting, snapping, and reconnecting in ways that even the most advanced scientific models struggle to predict. At the same time, a visitor from another star system is quietly entering this electromagnetic ocean. Its name is Threeey Atlas, and its presence is already rewriting what we thought we knew about the balance of order and chaos in our solar system. For scientists, this is a moment of opportunity. An interstellar object carrying chemistry and structures born under an alien sun has arrived in our neighbourhood. For others, it's a source of unease, even paranoia. Magnetic disturbances on Earth are increasing. The Sun is awakening from its quiet years. Power grids, satellites and navigation systems are being tested by storms of charged particles. And now, into this growing turbulence, an enormous plasma cloud carried by a foreign traveller is plunging into the Sun's magnetic domain. The tension between scientific certainty and cosmic anxiety has never felt sharper. Are we merely witnessing coincidence? Or are we entering a period when events that should be separate are converging into something far stranger? Stay with me on this late-night exploration as we begin to unravel the currents of energy threading through the solar system, the visitor that has wandered into them, and the unsettling patterns now rising on Earth. On July nights in 2025, the first whispers of disturbance came not from scientists but from the auroras. They stretched further south than expected, lighting skies over regions where most people had never seen them in their lifetimes. Electric greens shimmered over the Midwest of the United States, over Central Europe, over Japan. Amateur cameras caught colours rippling like curtains across the horizon. It was beautiful, but it was also a warning. The Geomagnetic Index, measured carefully by NOAA's prediction centre, had climbed high, triggered by a steady blast of solar wind from a coronal hole. That data on its own was nothing unusual, but the pattern of storms was becoming more persistent, more extended, and more complex than many forecasters expected for this stage of the solar cycle. The Sun was waking, and its outbursts were not coming in sudden violent flares, but in continuous high-speed streams that gnawed at Earth's magnetic shield day after day. At the same time, deep beneath the Pacific Ocean, seismographs were recording restless tremors. Kamchatka shook with one of the strongest earthquakes of the decade, an event powerful enough to shorten Earth's day by microseconds. Aftershocks cascaded across the region, and seismologists spoke cautiously about stress transfer, subduction zones, and tectonic inevitability. But outside of official reports, speculation began to leak into discussion boards, late-night talk shows, and eventually mainstream outlets. The timing between geomagnetic storms and seismic unrest was too close, some said, to ignore. Into this atmosphere of unsettled science and rising speculation came the discovery of Threeey Atlas. Detected by a wide-field survey telescope, it was quickly confirmed to be an interstellar object, the third ever recorded. Its hyperbolic orbit made it clear this was no local comet nudged by Jupiter, but a wanderer from deep interstellar space. Initial observation should have shown a dormant, frozen rock. Instead, the object was already active, already trailing gas and dust in a coma far larger than expected. That coma now spans hundreds of thousands of kilometres, a bubble of ionized particles half the size of the Sun itself. Think about that for a moment. A fragment of ice and dust, perhaps no more than a few kilometres wide, carrying with it an atmosphere that dwarfs the planets, is now colliding with the solar wind. Every second, charged particles from the Sun slam into that cloud, ionizing atoms, creating electric currents, and sending ripples through the heliosphere. And Earth is inside that same environment, shielded only by a magnetic field that is itself under pressure. Mainstream science is cautious here. The United States Geological Survey insists there is no causal link between geomagnetic storms and earthquakes. NOAA describes the space environment as dynamic, but within expected limits for solar maximum. But the coincidence of timing, the clustering of storms and quakes, and the presence of a massive interstellar plasma bubble are enough to make even seasoned researchers glance twice at their graphs. The uncertainty grows because our measurements are incomplete. Satellites orbiting Earth sample the solar wind at a single point, giving us a stream of data that tells us what is happening here, but not necessarily what is happening a million kilometers away. The interstellar object, with its enormous coma, is interacting with volumes of space far beyond what we can directly monitor. In a sense, it has become a natural probe, dragging through the solar wind, altering currents, and perhaps creating disturbances that ripple far downstream. To the human eye, the visitor is faint, visible only through telescopes, but electrically it may already be rewriting the currents flowing through the heliosphere. This is the heart of the tension. On the one hand, everything we observe can be explained within conventional science. Solar storms are expected during solar maximum. Earthquakes occur along stressed fault lines. Interstellar objects develop comas when volatile ices are exposed to sunlight. On the other hand, the convergence of all these phenomena within the same narrow span of months is something that cannot be ignored. We are left with two competing explanations. Either the universe has delivered us a coincidence of extraordinary proportions, or forces we do not yet understand are linking events across scales from the subatomic to the planetary. And so the story begins with the magnetic chaos rising around us. Earth's protective field, a bubble generated deep within the molten iron of the core, is being tested by streams of solar wind that strip away its stability. The visitor from another star has entered that environment, trailing a coma so vast it rivals the Sun in extent. Earth's systems, fragile by comparison, are showing signs of strain, from flickering power grids to restless seismic zones. Scientists know how to measure, how to catalogue, how to record. But in times like this, measurement alone feels insufficient. The real question is whether we are about to experience a shift in the balance of cosmic forces, or whether we are simply caught in the coincidence of cycles. As the days pass and the object drifts deeper into the inner solar system, that question will become harder to avoid. The forces at play are not hypothetical. They are measurable, even if we don't fully grasp their consequences. Magnetic reconnection events occur every day on the Sun, releasing bursts of plasma that race outward at hundreds of kilometers per second. When they reach Earth, they compress the magnetosphere, inject currents into the crust and disrupt communications. We call these disturbances storms, but they are not storms of air or water. They are storms of charged particles, of invisible fields, of pure energy. And now those storms are overlapping with the growing presence of an alien cloud. What does that mean for us? It may mean nothing more than spectacular auroras and exciting opportunities for astronomers. It may mean that October of 2025 will become a footnote in textbooks, a period of heightened activity but nothing more. Or it may mean that the convergence of a restless sun, a stressed Earth, and an interstellar intruder is about to produce phenomena we cannot yet predict. One thing is certain: the patterns of the past months are only the beginning. The Sun is not yet at the peak of its cycle. The object is still approaching perihelion. Earth's tectonic plates are still adjusting to the massive ruptures of recent earthquakes. The story is not ending here. It is only opening. As the visitor drifts closer to the inner solar system, something else has been stirring. Invisible forces, always present but rarely considered, are growing stronger and harder to ignore. Most people live their entire lives unaware that they are surrounded by magnetism on scales both intimate and cosmic. The tiny fields that align a compass needle are the same forces that shape entire planets, direct streams of plasma across millions of kilometers, and sculpt the boundaries of our solar system. These forces are not just background phenomena, They are the architecture of space itself, and they are awakening. For decades, Earth's magnetic field has been known to wander. The North Magnetic Pole has been racing across the Arctic Ocean, leaving maps and navigation systems struggling to keep pace. Geophysicists have debated whether this drift signals the beginning of a pole reversal, a process that has happened many times in geological history. At the same time, the strength of the field itself has been declining by fractions of a percent every year. On its own, this slow change would not raise alarms, but combined with the timing of solar activity and the arrival of an interstellar object, the picture begins to look more unsettled. To understand why, imagine Earth as a small electrical generator. Deep within the molten outer core, iron flows in swirling currents, creating a self-sustaining magnetic field that extends far into space. That field deflects charged particles streaming from the sun, forming a protective shield we call the magnetosphere. Normally, this system functions quietly, invisible except when solar storms make it flare with auroras. But when conditions change, when the solar wind becomes turbulent or when unusual plasma structures enter the heliosphere, the field reacts in ways we're only beginning to measure. During September of 2025, those measurements began to show strange patterns. Satellites recorded sudden dips in solar wind density, followed by surges in velocity. Ground-based magnetometers registered fluctuations that lasted longer than expected. The KP index used to track geomagnetic disturbances climbed again and again into storm territory. These were not isolated bursts, but sustained events, the kind that can leave power operators uneasy and pilots rerouting flights away from polar routes. At the same time, seismologists were logging clusters of earthquakes that refused to follow ordinary statistical decay. Aftershocks in Kamchatka and the broader Pacific Ring of Fire seemed to synchronize with periods of geomagnetic unrest. Official reports dismissed any causal connection, but the public noticed the timing. Online discussions filled with speculation, with graphs overlaying solar wind data onto earthquake charts. Some of the correlations were crude, but others were unsettlingly precise. This is where the idea of invisible forces awakening becomes more than just metaphor. If the Earth's crust is already stressed, if fault lines are already near failure, then even small external nudges could shift the balance. These nudges might come from tidal forces of the moon, from changes in atmospheric pressure, or, as some researchers cautiously suggest, from currents induced by geomagnetic storms. The principle is simple. A system near the breaking point does not need a shove, only a whisper. Enter Threeey Atlas. Its coma, already measured at more than 700,000 kilometers across, is not just gas and dust. It is plasma, ionized particles that interact directly with electromagnetic fields. As this massive bubble of charged matter moves deeper into the sun's influence, it becomes part of the solar circuit. It bends magnetic lines, alters currents, and creates disturbances that radiate outward. Earth, sitting 150 million kilometers away, is within reach of these changes. Skeptics point out that the energy scales do not match. A comet's coma, no matter how large, cannot rival the power of the sun itself. That is true. But again, the question is not about overwhelming force. It is about timing and resonance. Small changes, introduced at precisely the right moment, can cascade through complex systems. This is how bridges collapse from rhythmic vibrations, how circuits overload from tiny surges, how ecosystems shift from minor disruptions. The Earth-Sun system is no different. The awakening of invisible forces is being measured in ways most people never hear about. Very low-frequency radio stations, which bounce signals off the ionosphere, report unusual interference. Long-distance submarine cables detect tiny but measurable currents, flowing unexpectedly. Auroral researchers note that patterns once confined to high latitudes are spreading equatorward more often. All of these signs point to a system under pressure, a magnetic shield being tested from multiple directions at once. There is also the psychological awakening. Humans may not sense magnetic fields directly, but we are highly sensitive to patterns, coincidences, and disruptions to routine. When lights flicker during a storm, when auroras appear where they should not, when earthquakes cluster in unsettling ways people notice, the connection may not be proven, but the perception becomes part of the story. In the absence of certainty, speculation fills the gap, and speculation often points to hidden forces at work. History reminds us that this is not new. In earlier centuries, comets were seen as omens, harbingers of disaster. Their sudden appearance in the night sky, bright and unfamiliar, was interpreted as a message from the heavens. Today, we may understand their composition and trajectories, but the sense of unease remains. Threeey Atlas is not just another comet. It is a traveller from another star system, active at distances where ordinary comets remain inert, carrying a plasma envelope so large that it rivals our Sun. To say this has no effect on the solar system is to dismiss the evidence of its sheer scale. The invisible forces we are watching now are not omens but physical realities. They are currents of charged particles, distortions of magnetic fields, ripples in the heliospheric plasma. They cannot be seen, but their fingerprints are everywhere, from the glow of auroras to the hum of electrical grids. The visitor from interstellar space has entered their domain, and the timing could not be more provocative. Some researchers have proposed that interstellar objects may act as amplifiers. Their comas, when ionized, become conductive regions that can resonate with solar wind disturbances. In effect, they enlarge the interaction zone between the Sun and space, creating fluctuations that ripple outward more strongly than they would otherwise. If that is true, then Threeey Atlas is not a passive traveller, but an active participant in the Sun's electromagnetic drama. Its arrival, coinciding with solar maximum, creates conditions that have never before been observed in modern science. This is why the story matters. It is not about fear of impact or collision. The object poses no threat of striking Earth. The danger, if any, lies in its role as a catalyst, an amplifier of forces already in motion. Earth's magnetic field is drifting, its shield weakening, its tectonic plates restless. The Sun is surging, coronal holes and streams of high-speed plasma racing outward, and into this charged environment enters a massive interstellar plasma cloud, stirring currents in ways we are only beginning to detect. The awakening is not just happening in space. On Earth, researchers are logging anomalies in animal behaviour, in atmospheric electricity, in radio propagation. These may be coincidences, but they are piling up. Each anomaly on its own can be explained, but together they form a picture of a system shifting into a new state. Whether that state is temporary or the beginning of something larger remains unknown. The invisible forces that surround us are rising in strength and frequency. For now, they manifest as auroras, as flickers in data streams, as whispers in seismic charts. But the convergence of patterns suggests more may be coming. The visitor has only just arrived. The Sun has only just begun to stir, and Earth is only beginning to feel the tension. The currents are awakening, and their story is just starting to unfold. The idea that the solar system functions like a vast electrical circuit is not something most people ever consider, but the more we study it, the more that analogy proves difficult to ignore. Every star is a generator, producing a constant outflow of charged particles. Every planet with a magnetic field becomes a node in that circuit, interacting, absorbing, and sometimes even redirecting the flow. Between them, invisible currents stretch across billions of kilometers, forming a structure so immense that the human mind struggles to grasp its true scale. To live inside this system is to be immersed in currents of energy that never stop flowing. They pass through us, around us, above our heads, and deep below our feet. For most of human history, the solar system was imagined as a clockwork of orbits and gravity, mechanical in its nature and predictable in its timing. Gravity remains the anchor that holds planets to the Sun, but gravity alone does not explain the dynamics we observe. The Sun does not merely shine light, it breathes plasma. The Earth does not merely orbit, it resists, bends and shapes the wind of particles pouring outward. Jupiter's massive magnetosphere stretches so far into space that it influences regions millions of kilometers from the planet itself. When these forces connect, they create circuits on a cosmic scale. The heliosphere, the bubble of space controlled by the Sun's magnetic field, extends far beyond the orbit of Pluto. Within it, magnetic field lines twist into spirals, dragged by the Sun's rotation, carried outward by the solar wind. These lines are not static. They reconnect, they snap, and they shift, releasing bursts of energy that propagate outward at extraordinary speeds. When they intersect with planetary fields, currents are induced, sometimes minor, sometimes strong enough to power auroras visible from space. This is the circuitry of the solar system, never still, never silent, but continuous, dynamic, and immensely powerful. The arrival of an interstellar object like Threeey Atlas disrupts this circuit in ways that are not yet fully understood. Its coma is not a simple cloud of dust, it is a conductive plasma, responsive to electromagnetic fields. When it crosses the boundaries of the solar wind, it acts like a floating wire introduced into a circuit, altering currents and redistributing energy. The sheer size of its coma makes the effect difficult to ignore. At over 700,000 kilometers wide, the bubble is large enough to act as a new electromagnetic node in the system, one born not from planetary magnetism, but from the interaction between alien ices and solar radiation. We have hints of how such interactions might play out. Comets within our own solar system sometimes generate magnetic disturbances when their ion tails connect with the solar wind. These disturbances are usually small, transient and localized. But scale matters. The coma of Threeey Atlas is on an entirely different level, larger than most planetary magnetospheres. It drags against the current of the solar wind, creating turbulence, vortices, and possibly even shock fronts. Each of these disturbances has the potential to ripple through the circuitry of the heliosphere, eventually reaching Earth and other planets. Scientists measure this circuit through satellites positioned at key points. Instruments aboard missions like the Solar and Heliospheric Observatory and the Solar Orbiter record the speed, density and magnetic orientation of the solar wind. What they reveal is a system in constant flux, sensitive to even small changes in conditions. One of the mysteries that has emerged from these measurements is the sudden drop in solar wind density that sometimes precedes major geomagnetic storms. These so-called magnetic vacuums seem to act like an opening in the circuit, a sudden lowering of pressure that allows energy to surge through more forcefully once the gap is filled. The idea that an interstellar plasma coma could contribute to these vacuums is speculative, but not implausible. If the coma acts as a sink for particles, absorbing solar wind ions before they continue downstream, then regions of low density could appear where otherwise none would exist. Earth, sitting within the path of the solar wind, would then experience not only changes in magnetic orientation but also changes in the flow itself. These alterations could manifest as geomagnetic storms, currents induced in the crust, and disturbances in the ionosphere. On Earth, the impact of this circuitry is felt in many subtle ways. Submarine communication cables experience electrical surges during geomagnetic storms. Pipelines corrode more quickly when currents flow through the ground. Radio signals bounce unpredictably as the ionosphere swells and contracts under the influence of space weather. Even migratory animals, sensitive to magnetic cues, can lose their bearings during strong disturbances. Each of these effects is a reminder that the solar system's circuit is not an abstract idea, but a physical reality with tangible consequences for daily life. The hidden circuitry also helps explain why planetary alignments sometimes coincide with unusual electromagnetic activity. From a purely gravitational perspective, the alignments of planets should have almost no measurable impact on Earth. The forces are too weak and too distant. But electrically, the picture changes. Each planet with a magnetic field connects to the solar current sheet, the vast spiral of electrical flow emanating from the Sun. When multiple planets align, their combined influence can alter the impedance of the circuit, subtly reshaping the way energy flows through the heliosphere. The effect is difficult to measure directly, but patterns in space weather suggest that alignments are not always meaningless. They may act as modifiers, tilting the balance of currents just enough to create stronger or weaker disturbances when the solar wind interacts with Earth. This hidden circuitry also reveals why the Earth's weakening magnetic field has become a source of concern. If the shield protecting the planet from solar particles is thinning, then the same level of space weather's disturbance may produce greater impacts. Currents that once dissipated harmlessly in the upper atmosphere may now reach further downward, into the crust, into human infrastructure. The interstellar visitor arrives in the midst of this weakening, at a time when the circuit is already vulnerable. The timing could be coincidence, or it could be the beginning of a feedback loop that ties solar activity, interstellar plasma, and Earth's magnetic state together in unpredictable ways. One of the more unsettling questions is whether the circuitry of the solar system can influence not just electromagnetic systems, but geological ones. If induced currents alter the balance of stresses along fault lines, if electromagnetic surges change the behavior of fluids deep within the crust, then the boundary between space weather and earthquakes becomes blurred. Most seismologists reject the idea outright, but a minority continues to explore it, pointing to patterns of timing that appear too close to be random. The circuit of the solar system may not end at the magnetosphere. It may extend into the ground beneath our feet, linking space to seismic unrest in ways that remain unproven but not impossible. Looking ahead, the circuit will be tested as never before. Solar maximum approaches, promising more storms, more eruptions, more coronal holes. The interstellar visitor continues to expand its coma, injecting new turbulence into the solar wind. Earth's field continues to weaken, drifting steadily toward uncertainty. Together, these factors form a network of conditions that amplify one another. A stronger sun meets a weaker Earth. A foreign plasma cloud meets a stressed tectonic system. The hidden circuitry that normally hums quietly in the background is beginning to roar. It is tempting to dismiss these ideas as speculation, but even speculation has its place when data is incomplete. We know that the sun's magnetic field extends far beyond what we can measure directly. We know that plasma interactions scale in non-linear ways, producing outsized effects from small triggers. And we know that interstellar objects like Threeey Atlas are not theoretical. They are real, they are here, and they are active. In the interplay of these truths lies the possibility that the solar system's circuitry is not just hidden, but awakening, reshaped by forces we're only beginning to recognize. The evidence will accumulate in the months ahead. Instruments will record new surges, new anomalies, new disturbances that may or may not fit the models we currently use. Each new data point will be a clue, a fragment of a larger picture. Whether that picture confirms conventional expectations or forces us to rethink the way the solar system operates, it will be assembled piece by piece, surge by surge, storm by storm. The current is flowing, the circuit is alive, and with each passing day the presence of the interstellar visitor becomes more entangled in its design. When an interstellar object crosses the invisible boundary of the heliosphere, it enters a domain unlike any other in the galaxy. The heliosphere is the sun's shield, a vast bubble of plasma and magnetic fields that stretches far beyond the outer planets. It is not empty space, but a frontier zone, a region where the solar wind collides with the thin breath of the galaxy itself. To breach it is to step from one environment into another, from interstellar medium into the charged environment shaped by a living star. In late 2025, Threeey Atlas is doing exactly that. Most comets that originate from our own solar system slip in quietly. They travel from the Oort cloud or the Kuiper belt, long arcs that bring them from frozen darkness into sunlight. Their arrival is not a breach, but a return, a homecoming of sorts. Threeey Atlas is different. It does not belong here. Its speed and trajectory confirm that it comes from beyond the reach of our sun's gravity. It has drifted for millions, perhaps billions of years through interstellar voids, a relic of another star system, carrying the chemistry of an alien nursery. Its entrance into the heliosphere is not just another cometary passage, but an incursion by an outsider, and its effects may ripple far beyond what we expect. The boundary it crosses is known as the heliopause. At this frontier, the outward flow of solar wind slows, compresses, and finally yields to the pressure of interstellar plasma. Voyager 1 and Voyager 2 are the only spacecraft to have crossed it, both sending back data that revealed how sharp and turbulent the boundary truly is. The solar wind, flowing at hundreds of kilometers per second, suddenly collides with interstellar matter, creating shocks, waves, and unexpected structures. It is into this charged, shifting environment that Threeey Atlas has entered. Its coma, already larger than most planets, collides directly with the edge of the solar bubble. This collision is more than symbolic. Plasma physics teaches us that when two regions of differing density and magnetic orientation meet, currents are generated. Magnetic reconnection events release energy, particles are accelerated, and turbulence spreads. In laboratory experiments, these processes produce arcs and surges of current. On the scale of the heliosphere, the same principles operate, but on a canvas measured in billions of kilometers. A conductive bubble like the coma of Threeey Atlas, dragged into this environment, cannot remain passive. It is charged, it is active, and it is now part of the sun's circuit. Already, subtle anomalies are being detected. Instruments designed to track the interplanetary magnetic field have recorded sudden shifts, brief reversals in orientation that appear too sharp for ordinary fluctuations. Some scientists attribute these to coronal mass ejections or coronal hole streams, both common during solar maximum, but others point to timing. The anomalies coincide with the projected entry of Threeey Atlas into the heliosphere, suggesting that its vast plasma environment may be interacting with the solar wind in ways not fully understood. On Earth, the effects manifest as geomagnetic storms of unusual persistence, not necessarily the strongest on record, but storms that last longer, storms that refuse to fade quickly, auroras that stretch further south than expected, interference patterns in long-wave radio that resist conventional explanation. Submarine cable operators report induced currents persisting for days instead of hours. These are subtle, easily overlooked by the public, but to researchers who track space weather, they stand out. Something is modifying the flow. Something is amplifying the turbulence. The breaching of the heliosphere by an interstellar plasma cloud also raises questions about scale. The coma of Threeey Atlas measures hundreds of thousands of kilometers across, comparable to the Sun itself. Its density is low, but density is not the only factor in electromagnetic interaction. Size, conductivity, and ionization matter just as much. A bubble this large acts like a sail, catching and redirecting currents that would otherwise stream unimpeded. It does not need to rival the Sun's output to matter. It only needs to introduce turbulence at the right points, and the system itself magnifies the effect. Imagine throwing a pebble into a river. The pebble is small compared to the flow, but it creates eddies, ripples, and waves that extend far downstream. In this analogy, the river is the solar wind, and the pebble is not a rock, but a vast cloud of plasma tens of times wider than Earth. The ripples it creates are not water waves, but magnetic disturbances travelling at hundreds of kilometers per second. Earth, downstream, is within reach of these disturbances. Breaching the heliosphere is also a test of what the interstellar medium carries. The coma of Threeey Atlas does not only interact with the solar wind, it also samples the galactic environment, carrying with it particles and fields from outside the Sun's domain. To scientists, this is invaluable. To a nervous public, it is unnerving. Material forged under another star is now mixing with our Sun's outflow. The potential for unique chemistry, rare isotopes, or exotic plasma conditions is real. These could provide insights into star formation and galactic processes. But they could also alter the dynamics of the heliosphere in ways we are unprepared to predict. There is also the question of memory. The heliosphere is not static. It retains traces of what passes through it. Dust, plasma, and magnetic disturbances do not vanish instantly but linger, sometimes for years. If Threeey Atlas introduces turbulence now, the consequences may echo long after it has left. The circuits of the solar system are not quick to reset. They store energy, they redistribute it, and they sometimes release it in bursts far removed in time from the original trigger. On Earth, such delays make causation difficult to prove. An earthquake following a geomagnetic storm may be dismissed as coincidence, even if the two are connected by a chain of subtle influences. A power outage weeks after a solar wind anomaly may not be traced back to the disturbance that initiated it. This is the challenge of living inside a system where cause and effect stretch across vast distances and timescales. The breach of the heliosphere by an interstellar object may already be shaping events, but proof will be elusive. Some researchers speculate about even broader implications. If interstellar objects enter the heliosphere regularly, they may be one of the hidden drivers of long-term solar variability. Their comas, acting as temporary nodes in the circuit, may contribute to cycles we do not yet understand. Solar activity has always followed an 11-year rhythm, but embedded within that rhythm are longer, less predictable fluctuations. Could interstellar intruders be one of the missing variables? The idea is provocative but not easily dismissed, especially now that we're observing one in real time. What makes the breach of the heliosphere by Threeey Atlas so compelling is not just the science, but the timing. The Sun is entering its peak activity for the cycle. Earth's magnetic field is weakening and drifting. Seismic systems are restless. Human infrastructure is more vulnerable to electromagnetic disruption than at any point in history. Satellites, grids, communication networks all depend on stability in a system that is anything but stable. Into this moment, an alien plasma cloud arrives, breaching the Sun's domain, altering its circuits, and sending ripples toward Earth. This is not an extinction-level threat. The object will not collide with our planet. But it is a stress test unlike any we have faced before. A test of how the solar system responds to an intruder. A test of how Earth's shield holds under pressure. A test of how interconnected cosmic forces truly are. Whether the outcome is benign or disruptive, it will not be invisible. The breach has already begun, and the evidence is accumulating day by day. The story now moves forward with urgency. The visitor is not slowing down. Its coma is expanding. The Sun is flaring more often. Earth's magnetosphere is recording disturbances that defy simple explanations. The heliosphere, once thought of as a protective bubble, is proving to be a living system, one that reacts to intrusions with turbulence that spreads across billions of kilometers. Threeey Atlas has breached it, and the consequences are unfolding in real time. The Sun has always been seen as a sphere of fire, a ball of burning gas so hot that it dominates every aspect of life on Earth. But fire is not an accurate description. The Sun is not burning in the way a campfire burns. It is a nuclear furnace, yes, but it is also something else entirely. An engine of plasma threaded with currents, filaments, and magnetic arcs that act like veins of electricity on a scale almost too vast to comprehend. To understand why the arrival of an interstellar object matters, you have to understand how the Sun itself conducts and channels energy through these invisible veins. Everywhere across its surface, loops of plasma rise and fall, guided by magnetic field lines. These are prominences, arcs of glowing matter lifted from the Sun's photosphere into its corona. They trace the Sun's electrical skeleton, showing where currents are strong and where they reconnect. Sunspots, dark patches that look like blemishes through telescopes, are in fact regions of concentrated magnetic activity, places where the field twists so tightly that energy is forced outward explosively. When the pressure becomes too much, these regions release solar flares, bursts of radiation that can travel across space in minutes, and coronal mass ejections, clouds of plasma so large they dwarf the Earth. These structures are not random. They form along the Sun's electrical pathways, channels that act like veins, carrying energy from deep within the convective zone out into space. Plasma physics reveals that charged particles are never distributed evenly. They move in filaments, in streams guided by magnetic fields. On Earth, we see this in lightning, in auroras, in power lines. On the Sun, the same principle applies, but the scale is titanic. A single solar flare can release more energy than all of humanity consumes in a year. A coronal mass ejection can eject billions of tons of plasma into the solar wind, reshaping the currents of the heliosphere. It is within these veins that the story of Threeey Atlas becomes most interesting. The interstellar object has entered a system already alive with currents. Its coma, filled with ionized gas, is not a passive observer, but a participant in this electrical web. The solar wind flows through it, altering its shape, pulling ions into long tails that extend for millions of kilometers. But this is not a one-way interaction. The cometary plasma interacts back, disturbing local currents, redirecting flows and potentially altering the balance of the Sun's electric veins. Some researchers argue that the Sun should not be seen only as a nuclear reactor, but also as an electrical system. This is not fringe speculation, it is a recognition of the fundamental role magnetism plays in solar dynamics. The Sun's rotation, combined with the movement of plasma beneath its surface, generates a complex magnetic field that flips polarity every 11 years. This cycle drives the waxing and waning of sunspots, flares, and coronal outbursts. The entire solar system is tied into this rhythm because the solar wind carries the Sun's magnetic field outward in spirals. Every planet, every moon, and now an interstellar intruder must interact with this vast electrical pattern. What makes the veins of the Sun so unpredictable is their tendency to reconnect. Magnetic reconnection is a process where twisted field lines snap into new configurations, releasing pent-up energy in violent bursts. This is what powers the most dangerous solar storms. When reconnection occurs on the side of the Sun facing Earth, the effects can be immediate. Geomagnetic storms, satellite malfunctions, power grid surges, and auroras. When it happens on the far side, the energy still radiates into the heliosphere, altering the background conditions that Earth inhabits. The arrival of Threeey Atlas, with its vast plasma envelope, could change where and how often such reconnections occur, introducing turbulence that modifies the rhythm of the Sun's electric veins. There are already signs that something unusual is happening. In recent months, solar observers have reported a clustering of active regions across the solar disk, producing back-to-back flares that chain together rather than appearing as isolated events. This chaining effect is unusual, suggesting that the magnetic field lines are interacting across larger distances than expected. Some scientists attribute this to the natural peak of solar activity. Others quietly wonder if the addition of an interstellar plasma mass to the heliosphere has shifted the balance, making the Sun's electric veins more unstable. For Earth, the difference matters. If the Sun's electrical activity becomes more interconnected, storms may become more prolonged, more global in their impact. Instead of isolated bursts, we may experience sequences of disturbances that test the resilience of modern infrastructure. Satellites, already vulnerable, may face repeated onslaughts. Power grids, particularly in high-latitude regions, may suffer from prolonged induced currents. Aviation and shipping, reliant on precise navigation, may experience repeated disruptions. Each event on its own is manageable, but the accumulation wears down systems not built for constant strain. The veins of the Sun also play a role in cosmic ray modulation. Normally, the solar wind deflects high-energy particles from outside the solar system, shielding Earth from their full intensity. But when the Sun's field weakens or becomes chaotic, more cosmic rays penetrate. This has measurable effects not only on electronics but on human health, particularly for astronauts beyond Earth's protective magnetic bubble. The intrusion of Threeey Atlas into the heliosphere may alter this balance, disrupting the shielding effect, allowing waves of galactic particles to reach Earth in greater numbers. These particles ionize the atmosphere, affecting cloud formation, possibly even climate, though the connections remain debated. The electric veins of the Sun do not stop at the corona. They extend outward, woven into the solar wind, carried past Mercury, Venus, Earth, and beyond. Each planet encounters them differently. Mercury, with almost no atmosphere, is bombarded directly. Venus, with no magnetic field, has its atmosphere stripped at the edges. Earth, with its magnetic shield, diverts most of the flow, but not without consequence. The disturbances travel along magnetic lines into the polar regions, where they ignite the auroras. Jupiter, with its immense magnetosphere, diverts enormous amounts of current, even generating its own auroral storms independent of the Sun. Now, Threeey Atlas enters this circuitry, a plasma body the size of a star's corona, and its influence cannot be dismissed. Consider the possibility that the Sun's veins are not fixed but responsive to what enters their domain. Just as the human body circulation can be affected by foreign particles, blockages, or changes in pressure, the Sun's electrical circulation may react to the presence of a massive conductive coma. The analogy is imperfect but suggestive. Even if the object does not rival the Sun in power, it may act as a disturbance, a clot in the flow, a redirector of current that shifts the balance of the system. Earth, dependent on that balance, experiences the consequences downstream. The importance of this becomes clearer when you realise how interconnected the Sun's electrical activity is with life on Earth. Agriculture depends on climate stability, which in turn is influenced by solar variability. Communication depends on satellites that orbit within the Sun's field. Transportation relies on navigation systems vulnerable to solar storms. Even the rhythms of human psychology are tied subtly to the cycles of light and magnetism. The electric veins of the Sun do not just shape the cosmos, they shape human civilization. And those veins are now being tested by the intrusion of an interstellar presence. Some may argue that this perspective overstates the role of Threeey Atlas, that the Sun's activity would surge with or without it. That is true to an extent. The solar cycle is a natural rhythm, but the addition of an external plasma mass at precisely this moment introduces variables we have never observed. Science advances not only by studying isolated systems, but by witnessing rare convergences. The coincidence of solar maximum, Earth's weakening field, and the breach of the heliosphere by an alien coma is such a convergence. To ignore it would be to miss an opportunity to learn how the Sun's veins truly behave under stress. In the weeks and months ahead, astronomers will track the solar wind with greater attention, searching for signs of anomalies that cannot be explained by ordinary solar processes alone. They will look for shifts in the interplanetary magnetic field, for prolonged disturbances, for storms that seem to outlast their causes. Each anomaly will be a clue to how the Sun's electric veins are responding to the presence of Threeey Atlas. Some may prove to be coincidences, others may reveal patterns that change our understanding of the heliosphere itself. What is clear is that the Sun is not a passive backdrop. It is a dynamic, electrically alive system, and its veins of plasma and current are sensitive to intrusion. The visitor from another star has entered those veins, not directly, but through the solar wind that connects everything in the heliosphere. The coming months will show whether the Sun responds with indifference or with turbulence that cascades through the solar system. The veins are alive and they are stirring. When most people think of storms, they imagine thunderclouds, lightning, rain and wind. But above the Earth, far beyond the troposphere where weather takes place, a different kind of storm rages. These are storms of energy, storms of invisible particles hurled outward from the sun, storms that strike not with rain but with magnetism. Geomagnetic storms are not seen directly but are felt everywhere, in the glow of auroras, in the disruption of radio waves, in the flicker of power grids, in the sudden silence of satellites. And now, as Threeey Atlas deepens its intrusion into the heliosphere, these storms are taking on new shapes and new intensities, forcing humanity to reckon with their power in ways most of us never expected. At the heart of a geomagnetic storm is the interaction between the solar wind and Earth's protective shield. The magnetosphere is a cocoon generated by the flow of molten iron in Earth's core, extending tens of thousands of kilometers outward into space. Normally it deflects the solar wind, diverting particles around the planet. But when the sun releases a surge of plasma, whether from a coronal mass ejection, a flare, or a high-speed stream from a coronal hole, the balance tips. The shield bends, compresses, and sometimes cracks open, allowing currents of charged particles to funnel down magnetic field lines into the upper atmosphere. This process is not abstract. When particles pour into the polar regions, they collide with atoms of oxygen and nitrogen, releasing light. To the human eye, this is the aurora, shimmering curtains of green, red, and violet that dance across the night sky. Beautiful, hypnotic, and to some, unsettling. For millennia, auroras have been interpreted as omens, portents of change, even spirits walking the heavens. Today we understand their physics, but the sense of awe remains. They are the most visible sign of geomagnetic storms, a reminder that Earth lives within a sea of energy. But auroras are not the only consequence. Hidden beneath their beauty are currents that spread across the planet. During strong storms, electric fields are induced in the crust, pushing currents through pipelines, cables, and transformers. In March 1989, one such storm collapsed the power grid of Quebec, plunging millions into darkness within seconds. Transformers overheated, systems tripped, and operators were left helpless. That storm was triggered by a coronal mass ejection, a cloud of plasma hurled from the sun at millions of kilometers per hour. Today, our infrastructure is even more dependent on electricity, even more vulnerable to disruption. Satellites too feel the brunt of these storms. Charged particles accumulate on their surfaces, leading to discharges that can fry delicate circuits. Navigation systems lose accuracy as the ionosphere becomes turbulent, distorting signals from GPS satellites. Communication links falter as radio waves scatter unpredictably. Even the International Space Station must take precautions, shielding astronauts from surges of radiation that pass through the magnetosphere's cracks. Each storm is a reminder of how fragile our technological cocoon really is, how dependent we are on stability in an environment that is anything but stable. Now add to this the presence of Threeey Atlas. Its coma, immense and electrically active, has become a new obstacle in the solar wind. As the sun's currents flow through it, turbulence spreads, ripple effects propagate, and the storms that reach Earth become less predictable. Not necessarily stronger in magnitude, but stranger in duration and timing. Instead of a single pulse of energy, disturbances linger, refusing to fade as quickly as models predict. The result is not just a storm, but a series of aftershocks in space weather, echoes that test the resilience of human systems in new ways. In recent months, power grid operators have quietly issued internal warnings. They're not speaking of apocalyptic collapse, but of heightened risk. Transformers are being monitored for unusual heating. Engineers are revisiting protocols for rapid shutdowns. Satellite operators are running simulations of prolonged geomagnetic activity, testing how long spacecraft can remain functional in elevated particle environments. Aviation authorities are preparing contingency plans for rerouting flights, particularly those that cross polar routes where exposure is greatest. To the public, these preparations are invisible, but behind the scenes, a sense of unease is spreading. For ordinary people, the impact is less direct but no less real. A geomagnetic storm can disrupt cell phone service, interrupt streaming, delay financial transactions, and cause glitches in digital networks. These are minor inconveniences when isolated, but during prolonged storms they can accumulate into systemic strain. Imagine a day when GPS signals flicker in and out, when credit card networks stall, when flights are delayed across entire continents, when news broadcasts struggle with satellite interference. None of these scenarios require science fiction. They are within the realm of what geomagnetic storms have already done. The difference now is that the triggers may arrive in sequences, extended by the turbulence introduced by an interstellar coma. There is also a more subtle human dimension. Some researchers have explored correlations between geomagnetic storms and human health, noting spikes in blood pressure, irregularities in heart rhythms, and even shifts in mood during strong disturbances. The mechanisms remain debated. Ionization in the atmosphere, disruption of melatonin cycles, or indirect effects through stress. But the patterns are intriguing. If storms become more frequent or more prolonged, the human world may feel their influence not only in technology, but in bodies and minds. Historically, societies have often interpreted geomagnetic disturbances as supernatural. The Norse saw auroras as reflections of shields in battle. Indigenous cultures in North America saw them as ancestral spirits. Even in modern times, stories persist of people feeling uneasy or restless under auroral skies. Science explains the mechanics, but the psychological imprint remains. When storms ripple across the sky, they remind humanity of forces beyond control, forces that connect Earth to the Sun in ways that no wall, no border, no policy can alter. Now imagine that connection altered by an alien presence. A plasma cloud larger than the Sun itself has entered the system, changing the way currents flow, altering the timing of storms, introducing variables we have never observed before. To scientists, this is an unprecedented opportunity. To ordinary people, it may become a source of confusion, even fear, as disruptions multiply without clear explanation. Geomagnetic storms, once rare and isolated, may begin to feel like a new kind of weather, strange, invisible, and persistent. Governments are aware of the risks. Reports from agencies like NOAA and NASA warn of the potential for a Carrington-level event, a storm comparable to the Great Solar Storm of 1859 that set telegraph lines ablaze and lit the skies with auroras visible as far south as the Caribbean. In today's interconnected world, such an event could cause trillions in damage, crippling power and communication systems for weeks or months. Most experts agree that such storms are inevitable, though their timing is uncertain. The arrival of Threeey Atlas does not guarantee such an event, but it raises the probability of anomalies that could serve as precursors. It is important to recognize that geomagnetic storms are not destructive in themselves. They are energy, pure and vast, interacting with Earth's systems. The danger lies in the mismatch between natural processes and human infrastructure. The Earth has endured storms for billions of years. Life has adapted to their rhythms. It is only in the last century that we have woven a technological net so fine, so fragile, that storms can pull it apart with ease. The challenge before us is not to stop the storms, that is impossible, but to adapt, to harden, to anticipate. Whether we succeed may determine how disruptive the coming years will be. The presence of Threeey Atlas ensures that the storms we face will not follow the patterns of the past. Already, researchers note disturbances that linger beyond their triggers, anomalies that suggest a system under new influences. The Sun's activity is rising toward maximum. Earth's magnetic field is weakening and drifting. The interstellar object continues to expand its coma, spreading turbulence into the solar wind. Together, these factors create a perfect stage for geomagnetic storms unlike any we have recorded. And yet, there is opportunity here. By studying how storms behave under these conditions, we may unlock insights into the hidden circuitry of the solar system, the ways in which interstellar objects interact with stellar winds, the vulnerabilities of our own civilization. In the glow of auroras and the hum of transformers, in the flicker of satellites and the silence of disrupted radios, clues are waiting. Each storm is a data point, each anomaly a key. The challenge will be recognizing the patterns in time to respond. For now, the storms continue. They rise, they fall, they linger longer than expected. They whisper of forces beyond human control, of connections between stars and planets, of a cosmos alive with energy. Humanity lives within these storms, dependent on their rhythms, vulnerable to their extremes. And with the arrival of an interstellar visitor, the storms are entering a new chapter, one that will test not only our technology, but our understanding of the universe itself. There are times when the sun seems to grow quiet, when its steady outflow of plasma dips not in speed but in density, as though the very breath of the star is thinning. To instruments, these moments appear as sudden drops in particle counts, the solar wind falling to a whisper, a rare and fragile state in a system usually defined by turbulence and force. Scientists call them low-density solar wind events, but to those who study the sun, they are more than anomalies. They are warnings, precursors, signs that the delicate balance between solar output and interplanetary space has shifted. For most of the solar cycle, the solar wind is a constant stream of charged particles, electrons, protons, and alpha particles, flowing outward in all directions at hundreds of kilometers per second. This wind sculpts the heliosphere, forms the background of space weather, and determines how the Earth's magnetosphere flexes and bends. But when density drops, something unusual occurs. The pressure holding back the interstellar medium weakens. The Earth's magnetic field, instead of being compressed, expands outward, its boundaries stretching further into space. Satellites record sudden changes in magnetic orientation, radio signals scatter differently, and cosmic rays slip through more easily. It is as though the protective current of the sun falters, leaving Earth momentarily exposed. These whispers of low-density wind are rare but not unprecedented. In May of 1999, a historic collapse of the solar wind density left Earth's magnetosphere swollen to unprecedented size, triggering auroras at unusual latitudes. Spacecraft detected particle counts dropping to nearly zero for hours at a time. For a planet accustomed to a steady solar heartbeat, it was as if the rhythm had skipped, creating uncertainty and vulnerability. Similar events have been recorded in the years since, but always as isolated anomalies, quickly forgotten as the solar wind resumes its normal pace. Now, as Threeey Atlas drifts deeper into the heliosphere, the pattern is shifting. Instruments are detecting drops in solar wind density more frequently, accompanied by surges of turbulence afterward. To some, this is coincidence, a product of solar maximum, when variability is naturally higher. But others see a connection, a resonance between the interstellar plasma cloud and the sun's outflow. The coma of Threeey Atlas, immense and conductive, may be acting as a sponge, absorbing solar particles as they stream past, creating pockets of low density downstream. The Earth, sitting within this flow, experiences the effects as whispers of near silence, followed by echoes of storm. The implications are profound. Low-density solar wind events destabilize the balance between Earth's magnetic shield and the surrounding space environment. When the solar wind pressure drops, the magnetosphere inflates. When pressure surges back, it contracts violently. These oscillations can trigger waves of energy within the magnetosphere, waves that travel along field lines into the ionosphere and crust. In practice, this means geomagnetic disturbances that do not follow the usual storm profiles. Power grids feel unexpected surges. Satellites encounter unpredictable drag as the upper atmosphere swells and contracts. Navigation systems drift off course, not because of storms, but because of the silence between them. Consider the timing. Earthquakes in the Pacific Ring of Fire, unusual auroral expansions, prolonged geomagnetic disturbances, all occurring within weeks of recorded low-density solar wind events. The coincidence is difficult to dismiss. In a stressed system, silence can be as destabilizing as noise. A sudden absence of pressure can allow stresses to realign, only to snap violently when the flow resumes. Some researchers now wonder if the Earth's crust, already near breaking points along fault lines, may be influenced by these oscillations. The evidence is circumstantial, but the pattern is haunting. The whisper of low-density wind also carries a broader cosmic message. It reminds us that the Sun is not in control of space unchallenged. Its domain, the heliosphere, is shaped not only by its own outflow, but by the environment it moves through. The galaxy is not empty. It is filled with plasma, dust, and magnetic fields that press back against the Sun's wind. The heliosphere is a bubble in constant negotiation with its surroundings, sometimes expanding, sometimes contracting. When an interstellar object breaches that bubble, carrying its own plasma cloud, the negotiation changes. The solar wind falters, thins, and whispers where it once roared. For Earth, this is more than a curiosity. Our reliance on technology makes us vulnerable not only to violent storms, but also to subtle anomalies. A prolonged drop in solar wind density increases the flux of cosmic rays. High-energy particles that penetrate electronics trigger errors in computer memory and degrade spacecraft components. Airlines at high latitudes record elevated radiation doses for crew and passengers. Climate scientists monitor ionization in the atmosphere, searching for links between cosmic ray surges and cloud formation. Each low-density event becomes a natural experiment in how cosmic forces touch daily life. The psychological dimension cannot be ignored either. When auroras stretch into regions unaccustomed to them, when skies glow in places where people have never seen such lights before, the effect is striking. Social media fills with images, speculation spreads, and old myths resurface. People sense that something unusual is happening, even if they cannot explain it. The silence of the sun, the whisper of its faltering wind, becomes part of the cultural narrative, feeding unease and fascination alike. Looking ahead, the pattern seems clear. As Threeey Atlas continues its journey, the frequency of low-density solar wind events may rise. Each one will test Earth systems, from satellites to grids to human resilience. Each one will add to the data, offering clues about how interstellar plasma interacts with stellar winds. And each one will remind us that silence can be as powerful as noise, that absence can destabilize as much as presence. The whisper of the sun carries weight, and its meaning is only beginning to unfold. The question remains whether these events are natural fluctuations amplified by coincidence, or the direct signature of an interstellar disturbance. Science moves cautiously, demanding proof, replication, and measurable mechanisms. Speculation fills the gaps, pointing to the possibility that we're witnessing not just solar variability, but a new kind of interaction between stars and wanderers. Whatever the truth, the whispers cannot be ignored. They are recorded, measured, and felt. They are part of the story now, a story that grows more complex with every passing day. And as the whispers continue, humanity waits, caught between awe and anxiety, watching the skies for signs of what comes next. Long before satellites measured the solar wind, long before telescopes captured the glow of interstellar visitors, humanity looked to the ground beneath its feet to make sense of cosmic unease. The Earth shakes, mountains split, seas rise in waves, and people have always asked why. Earthquakes have been written into myth, into scripture, into folklore that try to explain the violence of a planet that otherwise seemed stable. What is striking when we study those accounts is how often people connected seismic events to the sky. In Japan, earthquakes were blamed on the thrashing of a giant catfish restrained only by divine power. In Greece, they were attributed to Poseidon, god of the sea and storms, striking the earth with his trident. In Mesoamerica, quakes were seen as signs of cosmic cycles ending, the destruction of one world before the birth of another. The ground moved, and the explanation was always tied to something larger, something celestial. Modern science has stripped away much of the mythology. We know that earthquakes occur because of stresses built up along tectonic plates, because of the subduction of crust beneath crust, because of faults locked until their tension finally releases. But even as we explain the mechanisms, the timing still raises questions. Why now? Why here? Why in clusters? These are the mysteries that statistics cannot fully soothe. For centuries, observers notice patterns. Earthquakes that seem to follow strange lights in the sky. Quakes that clustered after great storms. Quakes that arrived when comets blazed. These connections were dismissed as coincidence, the imagination of fearful societies. Yet, as we revisit the records, patterns emerge that echo with unsettling clarity today. Take the Lisbon earthquake of 1755, one of the most catastrophic events in European history. It struck on the morning of November the 1st, flattening much of the city, unleashing a tsunami and killing tens of thousands. Survivors described unusual atmospheric phenomena in the days before. The sky glowing at odd hours, strange colours rippling above the horizon. At the time, these were seen as divine warnings. Today, they could be interpreted as ionospheric disturbances, precursors to seismic rupture. Similar accounts exist from China, where chronicles describe earthquake lights, luminous flashes in the sky observed before or during major quakes. Modern geophysics acknowledges that piezoelectric effects and magnetic anomalies can create such lights when rocks are stressed to the breaking point. The ancients recorded them faithfully, even if they lacked the vocabulary of plasma and electrons. Now, in the present, we are seeing parallels. During the massive quake in Kamchatka earlier this year, amateur videos captured strange lights flickering in the sky minutes before the ground ruptured. Some dismissed them as power surges, transformers exploding. Others insisted they were natural atmospheric signatures of tectonic stress. Seismologists hesitate to draw conclusions, but the coincidence of luminous phenomena and seismic activity is difficult to ignore. When we place these modern accounts beside ancient ones, the resonance is undeniable. The Earth itself seems to glow when it breaks, a faint aurora of the crust that echoes the auroras of the sky. The parallels deepen when we consider timing with solar activity. Ancient Chinese records, meticulously kept over centuries, often mention that great earthquakes occurred during periods of unusual celestial disturbances, comets, eclipses, sunspots visible to the naked eye. Western observers wrote similar things during the medieval period. Today, we know that solar maxima produce more flares, more geomagnetic storms, more ionospheric turbulence. Whether these can directly trigger seismic events is still debated, but the clustering of records across cultures is striking. Again and again, earthquakes appear linked in human memory to times when the sky itself was restless. Enter Threeey Atlas. Its presence coincides with a period of seismic unrest not just in Kamchatka, but along the wider Pacific Ring of Fire. Clusters in South America, tremors across Japan, unusual swarms in Alaska. Officially, this is business as usual for tectonics, but historically the parallels are unsettling. Ancient societies would have seen the glowing skies of auroras, the sudden arrival of a bright comet, the shaking ground, and concluded that all were connected. Today, we separate them into disciplines: astronomy, seismology, space weather. But perhaps in doing so, we miss the larger picture, the interconnections that lie beneath the surface. One of the most famous ancient connections between sky and quake comes from the Oracle of Delphi. The site was chosen, according to legend, because of vapours that rose from a fissure in the ground, inducing visions. Seismologists now know that the region lies on a fault, one that periodically releases gases and tremors. Earthquakes in that region were seen not only as natural disasters but as messages from the gods, encoded in the earth itself. If we strip away the mythology, we are left with an ancient recognition that the earth and the sky speak to each other through disturbances. Today, we see the same dialogue in data. Solar wind presses against the magnetosphere, currents flow into the crust, and seismographs record unrest. The language has changed, but the connection remains. Modern parallels also extend into the way societies respond. The Lisbon quake reshaped European thought, fueling debates about divine punishment, natural law, and human vulnerability. Today, every major quake sparks debates about infrastructure, climate change, even cosmic influence. After Kamchatka, social media buzzed with speculation about the timing of auroras, about whether the sun's activity or the interstellar visitor had a role. Scientists pushed back, citing lack of evidence. But the public, like ancient peoples, seeks patterns, seeks meaning, seeks to connect the trembling of the earth with the restlessness of the sky. Perhaps what is most unsettling is that in both ancient and modern accounts, the sense of convergence is the same. When unusual lights appear, when comets blaze, when the ground shakes, people instinctively feel that these are not separate events, but part of one larger unfolding. Science provides mechanisms to explain each piece, but the convergence remains difficult to dismiss. The Earth may indeed be influenced by more than tectonic forces. The solar wind, the magnetosphere, even the plasma of an interstellar intruder may nudge systems already on the edge, triggering cascades we do not yet fully understand. As researchers revisit ancient records with modern tools, they find surprising consistencies. Chinese scholars have correlated solar cycles with earthquake frequency. Japanese archives show that some of the strongest quakes occurred near peaks of auroral activity. European chronicles align disasters with the appearance of comets. The ancients may have lacked scientific models, but their observations were precise. They saw what they saw, and they recorded it. Now, centuries later, we're rediscovering the parallels. In the present, the parallels continue to mount. Auroras glow at unusual latitudes. Low-density solar wind events create oscillations in Earth's shield. Earthquakes cluster in stressed regions, and an interstellar comet, carrying a plasma cloud the size of the sun, enters the system. The convergence echoes ancient times when sky and Earth seemed to move together, when disturbances above mirrored disturbances below. The only difference is that now we have instruments, data, satellites, graphs. But the unease, the intuition that something larger is at work, is the same. What matters most may not be whether the connections are proven beyond doubt. What matters is that they are being felt, noticed, recorded. Humanity has always sought to understand the patterns that shape its world, whether through myth, science, or speculation. Ancient earthquakes taught people to look upward for meaning. Modern quakes, unfolding alongside cosmic disturbances, are teaching us the same lesson again. The Earth does not tremble alone. It trembles within a web of forces that stretch from its core to the stars. When most people imagine a comet, they think of a frozen rock trailing a tail of ice and dust across the night sky. A bright point with a luminous streak visible for days or weeks before fading back into darkness. That picture, while iconic, is far too small for what is happening now. Threeey Atlas is not a modest visitor. It is not a silent speck drifting unnoticed. Around it swells a structure so vast that it dwarfs the planets, so immense that even the sun itself seems modest by comparison. Its coma, the cloud of ionized gas enveloping its core, has expanded until it stretches nearly half the width of the star that dominates our system. This is not just a spectacle, it is a physical event with consequences. A coma of such magnitude is not a passive fog. It is a plasma bubble, electrically conductive, reactive to every magnetic current and every particle stream it encounters. It is, in effect, a new presence in the circuitry of the solar system, one large enough to bend currents, to deflect flows, to stir turbulence on a scale our instruments have rarely been asked to measure. The expansion of this coma marks a new phase of the story, one where the interstellar intruder is no longer simply present but actively reshaping the environment it moves through. The size alone is staggering. Measured in hundreds of thousands of kilometers, the coma's radius surpasses that of Jupiter's magnetosphere, which itself can enclose multiple Earths. Imagine a bubble of ionized gas so large that if it were placed where the Sun is, its edges would stretch nearly halfway across the solar disk. This bubble is not glowing brightly in visible light. It is faint, ghostly, detected through instruments that measure ionization and charge, but its presence is undeniable. And because plasma interacts with magnetic fields, its presence is powerful. The expansion is driven by sunlight. As the comet approaches the inner system, volatile ices trapped in its nucleus vaporize, releasing streams of gas and dust. These molecules are then ionized by solar radiation, stripped of electrons, turned into plasma. Unlike neutral gas, plasma responds to electromagnetic forces, flowing along magnetic field lines, creating currents of its own. The larger the coma grows, the more solar particles it intercepts, and the more turbulence it injects into the solar wind. This is a feedback loop. Expansion feeds interaction. Interaction feeds turbulence. Turbulence spreads outward. Already, satellites monitoring the solar wind are recording anomalies consistent with such disturbances. Fluctuations in density, sudden reversals in the interplanetary magnetic field, unexpected persistence of geomagnetic storms. These anomalies cannot be explained entirely by solar flares or coronal holes. Something else is interfering with the flow, something large, conductive and present within the heliosphere. The timing aligns with the swelling of Threeey Atlas's coma, suggesting that the visitor's plasma envelope has grown into an active player in the dynamics of space weather. For Earth, the effects are indirect but real. Prolonged geomagnetic activity continues to test power grids and satellites. Auroras stretch southward more frequently, appearing in skies where they have no recent history. Radio operators report strange interference, patterns that resist conventional forecasting. Some see coincidence. Others, looking at the scale of the coma, see inevitability. A plasma cloud half the size of the Sun cannot pass through the solar wind without consequence. Its currents must connect, its turbulence must spread, its influence must ripple outward until Earth feels it. Historically, comets have carried an aura of unease precisely because of this scale. The ancients may not have understood plasma, but they saw the sudden arrival of a glowing cloud in the sky as a disruption to cosmic order. Today, we can measure that disruption, and the numbers are even more daunting than the myths. A coma spanning hundreds of thousands of kilometers is not a metaphor. It is an electromagnetic reality, capable of absorbing and redirecting energy flows that normally travel undisturbed. The question is, how long this phase will last. Comas grow as comets approach the Sun, but they can also fragment, collapse or dissipate if the nucleus is unstable. For Threeey Atlas, the outcome is uncertain. Its interstellar origin means we have no prior record of its behaviour. It has never passed this way before. Its composition may be unlike that of ordinary comets. Its stability is unknown. It could survive intact, expanding even further, or it could disintegrate suddenly, releasing bursts of plasma that ripple unpredictably through the heliosphere. Each possibility carries its own consequences. If the coma continues to expand, its interaction with the solar wind will intensify. potentially creating extended periods of turbulence that affect Earth. If it fragments, the release of material could create sudden shocks, brief but powerful disturbances in the solar system's magnetic environment. Either scenario tests our systems and our understanding. Either scenario reminds us that the presence of such a vast plasma cloud is not benign. Scientists face the challenge of separating coincidence from causation. The Sun is naturally active during solar maximum. Geomagnetic storms are expected. Earthquakes along tectonic boundaries are inevitable. To prove that Threeey Atlas is amplifying these events requires evidence, patterns that go beyond anecdote. But already, the persistence of anomalies is drawing attention. Already the parallels with historical records of comets and seismic unrest are being noted. Already, the expansion of the coma is rewriting the assumptions of how interstellar objects behave in the solar system. What makes the current moment so compelling is that all of this is unfolding in real time. Astronomers watch the coma expand through telescopes, measuring its ionization. Satellites feel the turbulence in the solar wind, recording data points that don't fit expectations. Power grid operators quietly prepare for disturbances they cannot predict. And ordinary people look up to see auroras glowing where they should not, sensing that something is different, even if they don't know why. The coma's size also raises philosophical questions. What does it mean for Earth to exist in a system where such immense, alien structures can suddenly appear? For centuries we imagined the solar system as stable, predictable, mapped. But the arrival of a plasma cloud half the size of the Sun challenges that perception. It reminds us that the cosmos is not static but dynamic, that order is always temporary, that intrusions from the interstellar void can reshape our environment at any time. There is no guarantee of catastrophe. The most likely outcome is a period of heightened turbulence, followed by the visitor's eventual departure back into the dark. But even without catastrophe, the lessons are profound. We are learning that interstellar comets are not curiosities but active participants in the electromagnetic systems of stars. We are learning that plasma, even at low densities, can influence flows on scales that matter to planets. We are learning that our technologies, our infrastructures, our very sense of stability are bound to forces we cannot control. The expansion of the coma is not just an astronomical event, it is a test of perspective. It forces us to recognise that our solar system is not isolated, that boundaries are porous, that the interstellar medium is not empty. It forces us to see the Sun not just as a source of light, but as a node in a larger electrical web, one now entangled with an alien cloud. And it forces us to admit that what happens hundreds of millions of kilometres away can ripple down into the smallest details of human life, from flickering lights to restless sleep beneath auroral skies. The coma continues to expand. The plasma cloud grows, half a star wide, carried deeper into the solar system. Its presence is a reminder that size matters, that scale changes everything. A comet's nucleus may be small, but its influence is vast. As it moves closer to the Sun, as it collides with stronger currents, as it bends the circuits of the heliosphere, the consequences will spread further still. We are inside those consequences now, living within the turbulence of a system reshaped by a visitor from another star. There are times when space seems not full, but empty, not turbulent, but still. In the records of solar wind data, these moments stand out as voids, stretches where particle counts collapse, where density drops almost to nothing, where the great current of the Sun falters as though something has pressed pause. Scientists call these intervals magnetic vacuums, rare episodes when the pressure of the solar wind collapses so drastically that the Earth's magnetosphere swells outward like a balloon freed from restraint. For decades they were curiosities, mysterious anomalies in a system we thought we understood. But as new disturbances ripple through the heliosphere with the arrival of Threeey Atlas, those old records are being revisited with fresh unease. The vacuum hypothesis was first raised after the May 1999 event, when spacecraft recorded a solar wind density so low that for nearly an entire day, Earth was almost unshielded by the pressure of particles we usually take for granted. Instead of compression, Earth's magnetic field expanded outward, reaching distances far beyond its usual boundary. Auroras appeared in unusual forms, radio propagation faltered, and cosmic rays surged through with greater intensity. The sudden absence of solar wind acted not as a relief but as a destabilization. Without the steady stream pressing against it, Earth's magnetosphere drifted into an unstable equilibrium, sensitive to every change, vulnerable to oscillation. What made that episode remarkable was not only the silence of the sun's outflow but the storms that followed. In the days after the vacuum, geomagnetic disturbances appeared that exceeded expectations given the apparent weakness of solar activity. It was as though the absence itself had primed the system, had created a tension that needed only the slightest nudge to cascade into turbulence. That observation led to the hypothesis that vacuums in the solar wind, rather than being benign, may in fact be dangerous precursors to storms, destabilizing the system by removing the very pressure that normally holds it in balance. For years, this idea remained speculative, noted in papers but rarely emphasized. Vacuums were too rare, too poorly understood, too difficult to study. But now, as the coma of Threeey Atlas expands and interacts with the solar wind, the pattern is re-emerging. Satellites are recording density drops not as singular anomalies but as repeated intervals, whispers of near-nothingness followed by turbulence. Each time the density falls, disturbances ripple outward afterward, stronger and stranger than expected. The timing suggests that the vast plasma cloud is interfering with the solar flow, absorbing particles, redirecting currents, and leaving stretches of near vacuum in its wake. The consequences for Earth are layered. When the solar wind drops, the magnetosphere swells. This expansion creates oscillations that ripple through magnetic field lines, travelling into the ionosphere and crust. These oscillations induce currents that reach into infrastructure, subtly but persistently stressing systems. When the solar wind resumes, the sudden compression releases that built-up oscillation in waves, amplifying disturbances. In this way, the vacuum acts as a spring, stretching the magnetosphere outward, then snapping it back with added force. The storms that follow are not merely natural but enhanced by the absence that preceded them. For seismologists watching the Pacific Rim, the parallels are troubling. Earthquakes do not require large external forces, only small nudges delivered at the right time to systems already near failure. If vacuums in the solar wind create oscillations in Earth's field, if those oscillations induce currents in the crust, then the timing of seismic swarms may not be entirely independent of cosmic conditions. It is not that solar activity causes earthquakes directly. It is that vacuums and storms act as nudges, amplifying stresses that are already near rupture. The pattern is subtle, but in recent months the coincidences have been difficult to dismiss. The vacuum hypothesis also carries implications for cosmic ray flux. During low-density events, the shielding provided by the solar wind weakens dramatically. High-energy particles from beyond the heliosphere pour in with greater intensity, ionizing the atmosphere, increasing radiation exposure at high altitudes, and potentially influencing cloud formation. Pilots and astronauts record higher radiation doses, electronics face increased error rates, and climate researchers wonder whether these surges can tip atmospheric patterns in subtle but meaningful ways. Each vacuum becomes not only a space weather anomaly, but a global experiment in how Earth responds to deep space radiation. When viewed through this lens, the expansion of Threeey Atlas's coma takes on a new significance. A plasma cloud half the size of the Sun is not simply a spectacle. It is a mechanism that may amplify vacuums by intercepting solar particles, by bending flows, by creating regions downstream where density collapses. Earth, orbiting within that downstream path, experiences the consequence as a sudden thinning of the solar breath. The timing, the persistence, and the strange resilience of storms afterward all point to a system now operating under new influences. For humanity, the practical meaning is clear. Our infrastructure is tuned to endure storms, but it is not tuned to endure silence followed by turbulence. Power grids are vulnerable to sudden surges, but they are also vulnerable to subtle oscillations that last longer than expected. Satellites can shield against bursts of radiation, but prolonged cosmic ray exposure degrades them more quickly. Airlines can reroute to avoid polar routes during storms, but they cannot avoid radiation increases during quiet intervals. In this way, vacuums become as disruptive as flares, not through force, but through absence. It is worth noting that ancient records describe silences too. Chroniclers wrote of skies that seemed strangely still, of stars that appeared sharper, of nights that glowed faintly before disaster struck. These accounts, while vague, align curiously with the effects of low-density solar wind. Clearer skies, unusual auroras, a sense of atmospheric stillness. The ancients may not have had instruments, but they observed with their senses, and they remembered what followed. Today, the parallels are emerging again. The silence of the sun, the whisper of a vacuum, is being felt not just in data, but in human perception. Scientists are cautious, as they must be. The vacuum hypothesis remains debated, and proof requires more data than we yet have. But the convergence of modern observations with ancient memory, the repetition of patterns across centuries, suggests that we may be rediscovering truths long intuited. The cosmos does not always speak with storms. Sometimes it speaks with silence, and that silence is just as powerful. The presence of Threeey Atlas ensures that the coming months will provide more opportunities to test this idea. Its coma will continue to absorb and redirect the solar wind, its plasma will continue to create turbulence, its influence will continue to ripple outward. Each low-density event recorded, each anomaly in the solar wind, will add to the evidence. Whether the vacuum hypothesis proves correct or not, the data will reshape how we understand the interplay between Sun, Earth, and interstellar space. For now, the vacuums continue to appear. The whispers of silence alternate with storms. The magnetosphere swells and contracts. The Earth trembles with quakes and glows with auroras. And humanity, caught between coincidence and causation, listens to the silence with unease. The vacuum is not emptiness. It is an influence, a force, a reminder that absence can be as disruptive as presence. And as Threeey Atlas moves deeper into the system, the vacuums may only grow more frequent, their consequences more pronounced, their meaning harder to ignore. Beneath our feet, the crust of the Earth is divided into plates, immense slabs of rock that grind against each other, colliding, subducting, and pulling apart. Their boundaries are fault lines, regions of pressure and release, zones where energy builds invisibly until it suddenly tears free. Earthquakes remind us that these lines are real, that the ground we treat as permanent is anything but stable. For most of history, they have been seen as purely geological, products of tectonics and mantle convection. Yet, as more evidence accumulates, a new picture emerges, one in which fault lines do not exist in isolation. They are immersed in a planet threaded by magnetism, a planet influenced by space weather, a planet that trembles not only because of forces below, but because of pressures from above. We live on fault lines in a magnetic universe. To understand this, one must first see the Earth as more than rock and water. Deep within its core, molten iron moves in convective currents, generating a magnetic field that extends far into space. This field shields the planet from solar wind, deflecting streams of charged particles and shaping a protective cocoon. But the shield is not perfect. It fluctuates with the sun's activity, compressing during storms, expanding during lulls, vibrating with currents that travel into the crust. These induced currents are not theoretical. They are measurable. Power lines hum with their influence, pipelines corrode more quickly under their stress, and instruments record their presence during geomagnetic disturbances. If technology feels them, the Earth itself must feel them too. Fault lines are already regions of instability where stresses are primed to release. Add electromagnetic currents, and you create the possibility of subtle nudges, triggers that may not cause quakes outright, but may influence their timing. This is the heart of the debate. Can magnetic disturbances act as catalysts for seismic events? Most seismologists dismiss the idea, arguing that the energy involved in tectonic processes dwarfs anything the sun could deliver. But a minority points out that scale is not the only factor. Systems near breaking point can be shifted by the smallest of forces. A lock can hold against tons of pressure, but a single key can open it. The Earth's crust may be no different. The records suggest intriguing patterns. The 1989 Quebec blackout, caused by a geomagnetic storm, occurred within days of a magnitude 6 earthquake in Alaska. The massive 2004 Indian Ocean quake, which unleashed a tsunami that killed hundreds of thousands, was preceded by unusual solar activity and low-density wind events. These may be coincidences. Yet, when one overlays decades of solar data with seismic records, clusters appear that challenge pure randomness. The timing is often close, sometimes within hours, enough to raise the question, not enough to claim certainty. Now with Threeey Atlas expanding its plasma cloud into the heliosphere, the patterns seem to sharpen. Geomagnetic disturbances persist longer than expected, seismic swarms follow unusual rhythms, and the overlap grows too precise to ignore. If the vacuum hypothesis suggests that absence in the solar wind can destabilize Earth's shield, then the magnetic universe hypothesis suggests that the induced currents in Earth's crust can reach fault lines, not as overwhelming force, but as whispers that push the already unstable past their threshold. The magnetic universe is not just a metaphor. Everywhere we look, magnetic fields shape matter. Galaxies spiral because of them, stars breathe plasma because of them, and planets shield themselves through them. Even our own brains operate with delicate electromagnetic patterns. To imagine that fault lines exist outside of this universal fabric is to underestimate the interconnectedness of nature. The same sun that lights our days also reaches into our crust with currents we barely understand. The same solar wind that sculpts auroras also induces stresses that pipelines and power grids cannot ignore. Why then should the crust be immune? Ancient records align curiously with this idea. Chinese scholars wrote of unusual sky glows before devastating quakes. European chroniclers noted comets and auroras appearing in the same years that cities were destroyed by tremors. Indigenous traditions often tied earthquakes to celestial events, whether stars falling, skies brightening, or gods battling above. These accounts, dismissed as myth, may reflect observations of magnetic phenomena coinciding with seismic upheaval. Today, we have the instruments to see the same parallels in data, but the sense of cosmic connection has not vanished. It lingers, now rephrased in scientific terms but still unsettling. In recent months, Kamchatka has shaken with repeated quakes, Japan has seen swarms along its coastal trenches, and South America has logged tremors in Chile and Peru. Each region lies along the Pacific Ring of Fire, the most seismically active zone on Earth. Each quake has coincided with periods of geomagnetic disturbance. The skeptics remind us that earthquakes are always happening, that coincidence is inevitable when comparing constant activity with frequent storms. But the clustering remains unusual, the parallels striking. Each event adds weight to the suspicion that we are not merely watching geology, but geology intertwined with cosmic magnetism. The expansion of the coma of Threeey Atlas raises the stakes. A plasma cloud half the size of the Sun is now part of the solar system's circuit. Its influence on the solar wind creates turbulence. Its absorption of particles creates vacuums. Its scale ensures that Earth is within reach of its effects. If induced currents can nudge fault lines, then the arrival of an interstellar plasma mass during a period of seismic unrest is more than coincidence. It is a confluence of forces, an alignment of instability above and below. The magnetic universe is speaking across scales, and Earth is listening whether we realise it or not. For humanity, this is both a challenge and a warning. Our societies are built along fault lines, both literal and figurative. Cities sprawl across coasts vulnerable to quakes and tsunamis. Power grids stretch across regions sensitive to geomagnetic storms. Digital networks link everything together, amplifying the consequences of any disruption. The magnetic universe does not distinguish between natural and human systems. It flows through both, shaping outcomes in ways we cannot fully control. What is needed now is awareness. Scientists must continue to explore the possibility that fault lines and magnetic fields are connected, not dismissing the idea simply because it challenges conventional boundaries. Engineers must prepare for the possibility that storms in space can ripple into the ground. And ordinary people must understand that the stability of their world depends on forces far beyond their sight. The ground beneath us is not separate from the sky above. Both are parts of one magnetic fabric, and both can tremble together. The story of fault lines in a magnetic universe is not about proving causation beyond all doubt. It is about recognizing patterns, about seeing the interconnectedness of systems once thought isolated. It is about acknowledging that the Earth is not an island of rock, but a conductor within a cosmic circuit. As the sun surges, as Threeey Atlas expands, as the Earth shakes, the parallels will only grow sharper. Whether coincidence or causation, the convergence cannot be ignored. The fault lines of our world are more than geological, they are magnetic, woven into a universe alive with currents. When the Earth trembles in one place, sometimes the ground shakes in another, far away, almost as though the planet itself is echoing the event across its surface. Seismologists have long recognised that large earthquakes can send waves racing through the mantle, circling the globe, converging on the point exactly opposite from where the rupture began. These Antipodal echoes are not always strong enough to cause destruction, but they are measurable, a reminder that Earth behaves as a resonant body. Like a bell struck on one side, vibrations ring out and concentrate on the other. In recent years, however, the echoes have seemed to grow louder, more pronounced, coinciding curiously with periods of heightened solar and geomagnetic activity. The physics of Antipodal echoes begins with seismic waves. When a major earthquake ruptures a fault, it releases energy in several forms. Primary waves travel fastest, compressing and expanding through rock. Secondary waves follow, moving in shearing motions. Surface waves, slower but more destructive, ripple outward along the crust. These waves do not stop at the boundaries of continents or oceans. They dive deep into the mantle, bending with changes in density, curving until they emerge on the far side of the planet. There, they converge, amplifying each other, creating measurable tremors even in places untouched by local faults. To sensitive instruments, these echoes are as clear as fingerprints. To the human senses, they are often imperceptible, unless conditions align to make them stronger. What makes this phenomenon fascinating is that the Earth does not always respond predictably. Sometimes antipodal echoes are faint, dissipating harmlessly. Other times they seem to trigger aftershocks or swarms near the convergence point, as though the energy of one rupture has the power to awaken stresses on the other side of the globe. In the past, this was considered coincidence, since tectonic stresses are everywhere. But as data has accumulated, the pattern suggests that echoes may matter more than once believed. In certain cases, large earthquakes appear to have antipodal companions, linked not by chance but by resonance. Now consider this resonance in a magnetic universe. The Earth is not only a mechanical body but also an electrical conductor, threaded by currents induced by space weather. When a geomagnetic storm strikes, those currents ripple into the crust, altering stresses in ways we're only beginning to study. Combine this with seismic waves converging at antipodes, and you have a recipe for amplification. A quake in one hemisphere may send waves across the globe, where they arrive just as currents surge through the ground, tipping an already unstable fault past its threshold. The result is an antipodal quake, not as a coincidence, but as an echo amplified by magnetism. The evidence for this interplay is growing. In 2010, after the massive Chilean earthquake, tremors were recorded near China, close to its antipodal point. In 2004, the Indian Ocean quake that triggered a devastating tsunami was followed by seismic unrest near South America, again near its opposite. Seismologists debate whether these are true causal echoes or simply coincidences in a restless planet. But the timing with geomagnetic activity is striking. Both events occurred during periods of unusual solar wind disturbances when Earth's magnetosphere was under stress. The echoes in this light may not be purely mechanical, they may be electromagnetic, shaped by conditions far above the crust. This brings us back to Threeey Atlas. Its massive coma is introducing turbulence into the solar wind, creating vacuums and storms that Earth experiences as prolonged disturbances. If these disturbances induce currents in the crust, then the Antipodal echo effect may be magnified. A quake in Kamchatka may ripple into South America with greater consequence. A rupture in Chile may send waves that awaken faults in Asia. The echoes may become more pronounced, not just mechanical vibrations but hybrid events, strengthened by the magnetic environment in which Earth is currently immersed. Ancient records again echo these ideas, though in different language. Chinese chronicles describe great earthquakes, followed by tremors on the far side of the world, as though they recognize the global nature of the Earth's response. Polynesian traditions speak of the planet shaking in pairs, one quake here, another there, as if the Earth was answering itself. Even Greek accounts describe quakes as the Earth groaning in resonance, one voice answered by another. To modern ears, these are myths. To a scientist aware of antipodal resonance, they are poetic descriptions of a real physical effect. What makes this effect so unsettling today is the convergence of conditions. Earth's magnetic field is weakening, its shield thinning, its poles wandering. The sun is at solar maximum, flaring and surging. An interstellar plasma cloud has entered the heliosphere, bending currents and creating turbulence. Together, these conditions ensure that every quake, every seismic wave, every echo will occur within a system already stressed. The antipodal effect may not be new, but the amplification is. We may be entering a time when echoes grow louder, when tremors speak across the globe with more force than before. The practical consequences of this are significant. If antipodal quakes become more common, then seismic forecasting must expand its scope. A rupture in one hemisphere may no longer be considered a localized event, but a potential trigger for instability on the other side. Engineers designing infrastructure in regions far from recent quakes may find themselves facing risks they once dismissed. Emergency planners may need to think globally, not just locally, when responding to seismic unrest. The Earth, under magnetic stress, may be more interconnected than we assumed. The echoes also carry a psychological weight. To ordinary people, the idea that a quake on the far side of the planet could cause one nearby is unsettling. It makes the Earth feel smaller, more fragile, more connected. Add to this the influence of auroras glowing in unusual skies, of satellites flickering under geomagnetic storms, of news about an interstellar comet the size of a star's corona, and the unease deepens. People sense that the planet is not isolated, that it responds to forces beyond itself, that tremors here are linked to disturbances above. Scientists remain cautious, as they must. The antipodal echo effect is measurable, but its connection to magnetism is still speculative. Yet, as the anomalies pile up, speculation begins to feel less like imagination and more like recognition. When Kamchatka shakes and South America trembles days later, when Chile ruptures and Asia stirs, when the timing overlaps with solar storms, the pattern becomes harder to dismiss. The echoes are real, and they're speaking louder. What Threeey Atlas adds to this picture is not only turbulence, but scale. Its coma is vast enough to alter the solar wind across enormous distances. Its plasma is conductive enough to resonate with magnetic fields. Its presence ensures that for months to come, Earth will live within a system unsettled by an alien cloud. Every quake during this time, every echo, every disturbance will unfold within this altered context. We are not merely measuring geology. We are measuring geology in dialogue with interstellar plasma. The echoes will continue. Some will be faint, barely detectable. Others may be strong enough to awaken faults. Each will remind us that the Earth is not separate from its environment, but immersed in a web of forces that extend across space. Each will show us that when the Earth shakes in one place, it may whisper or shout on the far side. The Antipodal echo effect is not a theory to be proven or disproven. It is a reality to be understood, a resonance to be respected, a reminder that the Earth, like the universe itself, speaks in rhythms across distance and time. Throughout history, people have looked to the heavens for patterns, convinced that the positions of the planets held meaning for life on Earth. In ancient Babylon, astrologers mapped the skies, linking alignments with the rise and fall of kingdoms. In medieval Europe, planetary conjunctions were read as omens of plague, war, or natural disaster. Even today, horoscopes trace their lineage to that ancient belief, that where the planets stand in the sky influences the fate of human beings. Modern science separated astronomy from astrology centuries ago, stripping away the mysticism. But what if the ancients, despite their limited framework, sensed something real? What if planetary alignments matter, not through mystical influence, but through physics and timing? In a gravitational sense, the influence of planetary alignments on Earth is negligible. Jupiter's pull on Earth is dwarfed by that of the Moon, and even when planets line up, the forces they exert are too weak to trigger earthquakes or storms. Yet gravity is not the only force at play. Each planet is also an electromagnetic body, immersed in the solar wind, connected to the Sun by magnetic field lines that stretch across millions of kilometers. Jupiter, with its immense magnetosphere, acts like a generator, channeling currents into the heliosphere. Saturn, Uranus and Neptune, though more distant, add their own contributions. Earth and Venus, closer to the Sun, interact with these currents differently. When the planets align, they do not merely line up in space. They align their electrical footprints within the circuitry of the solar system. This is where timing enters the picture. The solar wind is not uniform. It flows in spirals, carrying the Sun's magnetic field outward in a rotating pattern known as the Parker spiral. As it travels, it encounters planets, comets, and interstellar debris, each acting as nodes in the circuit. When planets align, their nodes can reinforce or interfere with each other, altering the impedance of the system, reshaping the way currents flow. These changes may be subtle, but in a system already near thresholds of instability, subtle shifts can cascade into turbulence. Historically, there are curious coincidences. The Great Lisbon earthquake of 1755, which destroyed one of Europe's most important cities, occurred within days of a significant planetary alignment. The eruption of Krakatoa in 1883, one of the most violent volcanic events in recorded history, was also preceded by alignments of multiple planets. The devastating 2004 Indian Ocean earthquake and tsunami occurred during a period when several planets clustered along similar longitudes. Skeptics dismiss these connections as cherry-picked correlations, the product of human pattern seeking. But the parallels persist, and when viewed through the lens of a magnetic universe, they gain a new dimension. Modern instruments show that planetary alignments can influence solar activity indirectly. During alignments, solar flares and coronal mass ejections appear slightly more likely. though the mechanism remains debated. Some theorize that tidal forces within the Sun, though weak, may interact with magnetic instabilities, tipping them toward eruption. Others argue that the alignments alter the flow of the solar wind in ways we do not yet fully model. Whatever the cause, the data hints at a connection. When planets align, the Sun sometimes responds, and when the Sun responds, Earth feels the effects. Now, into this already complex system, enters Threeey Atlas. Its coma, vast and conductive, acts like a new node in the heliospheric circuit. It does not orbit predictably like a planet. It cuts across the solar wind, dragging turbulence with it, altering currents in ways that planets alone do not. The timing of its arrival coincides with a period of notable alignments. Jupiter and Saturn in relative proximity, Venus and Earth crossing solar longitudes, Mars entering opposition. Each alignment modifies the circuit. Each alignment occurs in the presence of an alien plasma cloud. Together, they create a convergence of timing that no human has ever witnessed. Consider how resonance works in simpler systems. A swing pushed at the right moment goes higher with little effort. A bridge struck by rhythmic footsteps can collapse from vibrations alone. Small forces applied at precise intervals amplify the system's natural frequencies until they overwhelm stability. The solar system is no different. Planets align, currents resonate, the Sun flares, the solar wind surges. Earth, positioned downstream, absorbs the consequences. Add an interstellar plasma cloud into this resonance, and the amplification may grow stronger, the turbulence more unpredictable. This is not to say that planetary alignments dictate human fate in the way astrologers once claimed, but they may create conditions in which cosmic events cluster, in which the timing of storms, quakes, and anomalies is not entirely random. What the ancients intuited through observation, we may now be able to measure with data. The alignments they feared as omens may in fact be real markers of increased instability in a magnetic universe. Recent months offer examples. Auroras glowing far south coincided with planetary alignments in April and June. A swarm of quakes in South America clustered near the same period. Satellites recorded unusual interference, while power grids noted minor but persistent anomalies. None of these alone prove causation. Together they suggest timing worth watching. The alignment of planets, the expansion of a coma, the surge of solar activity, all converging into a window of heightened possibility. Looking ahead, October brings another convergence, a period when multiple planets align along the same solar longitude. By itself, this would be a curiosity. With Threeey Atlas active, it becomes more than that. The possibility of resonance grows sharper. The chance of anomalies increases. Scientists will watch the solar wind closely, scanning for drops in density, for reversals of the magnetic field, for storms that linger longer than expected. If patterns emerge, the case for planetary alignments influencing cosmic timing will gain weight, and the role of the interstellar visitor will become clearer. For humanity, the implications are both practical and philosophical. Practically, it means we must expand our forecasting. Geomagnetic models cannot ignore planetary positions if they prove to influence solar behaviour. Seismic risk assessments may need to consider alignments if correlations hold. Space weather predictions may need to account for the added turbulence of an interstellar coma. Philosophically, it means admitting that the ancients, in their own way, were right. The heavens do influence the Earth, not through mystical forces but through rhythms and resonances woven into the magnetic fabric of the universe. The alignment of planets is not rare, but alignment during the presence of an interstellar plasma cloud is unprecedented. This is a cosmic experiment, unfolding in real time, watched by satellites, recorded by seismographs, felt by power grids, seen in auroras. The timing cannot be dismissed. The universe is showing us its patterns, and for the first time, we have the instruments to see them clearly. The challenge is whether we will recognize the significance before the convergence passes. When people think of currents, they usually imagine rivers, streams of water rushing through valleys, winding toward the sea. But the universe is full of currents we cannot see, streams of energy and charged particles that weave through space in patterns more complex than any terrestrial river. In the Earth's oceans, turbulence defines the mixing of waters, shaping climates and ecosystems. In the solar wind, turbulence defines the mixing of plasma, shaping the space environment around every planet. To understand how the cosmos affects Earth, we must understand not just the steady flow of energy, but the secret life of turbulent currents that lie hidden within it. The solar wind is often described as a continuous outflow, a steady breath of particles expanding outward from the sun. Yet anyone who studies it closely knows this is an oversimplification. Embedded within that flow are shocks, waves, eddies, and vortices, chaotic patterns born from the sun's rotation, from magnetic reconnection, from collisions between fast and slow streams. These turbulent currents are not random. They carry structure across vast distances, forming filaments and sheets of plasma that can extend for millions of kilometers. When they reach Earth, they can compress the magnetosphere, stir its field lines, and inject bursts of energy that ripple down into the ionosphere and crust. It is within these turbulent patterns that much of the unpredictability of space weather lies. A coronal mass ejection may travel outward with a predictable velocity, but how its magnetic field interacts with Earth depends on the turbulence it encounters along the way. A high-speed solar stream may follow known paths from a coronal hole, but whether it triggers a major geomagnetic storm depends on the small-scale eddies that twist its field. In turbulence lies the difference between calm and chaos, between a minor aurora and a blackout. Now, with the arrival of Threeey Atlas, the turbulence is taking on a new complexity. Its coma, vast and conductive, is not a passive presence. As the solar wind flows past, it is disrupted, deflected, and tangled. Currents that once followed predictable paths are bent into new configurations. Turbulent eddies grow larger, shocks propagate differently, and downstream, Earth feels the consequences. Instead of storms that rise and fade predictably, we see disturbances that linger, storms that plateau instead of collapsing, anomalies that resist the models built on decades of data. The secret life of turbulent currents is becoming less secret, exposed by the amplification of an interstellar visitor. Scientists studying magnetohydrodynamics have long known that turbulence is more than noise. It contains nested structures, self-similar patterns that repeat across scales, from the eddies in a laboratory plasma to the filaments in a galaxy cluster. In this sense, turbulence is a universal fingerprint, a language spoken by systems as small as experimental reactors and as large as the cosmos itself. The turbulence in the solar wind is part of this continuum, and by studying it, we glimpse not only the behaviour of our star, but the behaviour of plasma everywhere. With Threeey Atlas reshaping those currents, we are seeing a natural laboratory unfold, one that cannot be replicated on Earth. For Earth, the practical consequences of turbulent currents are tangible. During recent storms, auroras have glowed further south than models predicted. Radio blackouts have lasted longer than forecasts suggested. Power grids have experienced unexpected surges during periods that should have been quiet. These mismatches point to turbulence as the culprit, currents weaving through the solar wind in ways that change how energy is delivered. To operators on the ground, the details of magnetohydrodynamic equations matter less than the reality of flickering systems. But for scientists, these mismatches are clues, signals that turbulence is not a side effect, but the main driver of unpredictability. The secret life of turbulence also extends beneath our feet. When geomagnetic disturbances ripple into the crust, they do not flow evenly. Just as rivers find channels in valleys, induced currents find channels in geological structures. Faults, mineral deposits, and variations in conductivity shape the path of these currents, creating hotspots where energy concentrates. Some researchers believe these hotspots may be linked to earthquake lights, luminous glows that appear before seismic events. Others suggest they may trigger microfractures that accelerate fault failure. Either way, turbulence in space translates into turbulence on Earth, a hidden link between solar wind and seismic unrest. Historically, unusual currents have often been linked to omens. Mariners reported compass needles swinging erratically before great storms. Farmers recorded strange lights in the sky before earthquakes. These observations, though dismissed for centuries, may have been early encounters with the secret life of turbulent currents. Without instruments, people relied on their senses, noting that the world felt different before catastrophe struck. Today, satellites provide the measurements, but the essence is the same. Turbulence alters the rhythms of the planet, and we notice, even if we do not always understand. The scale of turbulence is what makes it so formidable. A single eddy in the solar wind can span millions of kilometers. A shock wave can persist for days, traveling across the heliosphere like a storm in an endless ocean. When Earth sits within such a current, it is not a passive observer but an immersed body, influenced in ways both obvious and subtle. The expansion of Threeey Atlas's coma ensures that turbulence will be even more pronounced, as the solar wind now flows through a new obstacle, one large enough to alter currents across astronomical distances. This raises questions about resonance. If turbulence has structure, then it has frequencies. If it has frequencies, then some may match those of Earth's natural oscillations, amplifying effects just as a singer's voice can shatter a glass at the right pitch. Could it be that certain turbulent patterns resonate with Earth's magnetosphere, with its ionospheric currents, even with its seismic modes? The idea is speculative, but the physics allows it. Systems resonate when frequencies align, and the Earth is a resonant body. The secret life of turbulent currents may include hidden harmonies with our planet, harmonies that manifest as storms, quakes, or anomalies when the tuning is right. This perspective reframes ancient beliefs about cosmic influence. The astrologers who charted planetary alignments were, in their own way, searching for resonance. The myths that linked quakes to celestial events reflected an intuition that the Earth responds to forces beyond itself. Today we see those connections through data, through plots of solar wind density, through maps of auroral currents, through seismic charts. The intuition remains, now reinforced by science. The universe is turbulent, and turbulence matters. The coming months will provide more opportunities to witness this. As Threeey Atlas moves deeper into the system, its coma will continue to disrupt the solar wind. Turbulent currents will grow more complex, anomalies will persist, and Earth will remain immersed in the consequences. Each storm will carry lessons. Each mismatch between forecast and reality will reveal clues. Each aurora will glow as a visible marker of invisible chaos. Scientists will collect the data, but humanity will live the experience, feeling the turbulence in disrupted technologies, in restless skies, in the ground beneath their feet. The secret life of turbulent currents is that they are not truly secret. They have always been here, shaping the space around Earth, influencing our world in ways we rarely notice. What is changing now is our ability to see them, to recognize their patterns, to connect them with the anomalies that shape our lives. The interstellar visitor has made the currents louder, more obvious, harder to ignore. And in doing so, it has opened a window into the deeper reality of a universe where turbulence is the rule, not the exception. For as long as comets have been seen streaking across the sky, they have carried with them a certain unease. To ancient civilizations, they were messengers of disaster, celestial intruders whose presence coincided with plagues, wars, and the collapse of kingdoms. In modern times, science replaced superstition with the language of physics and chemistry. Comets became icy leftovers from planetary formation, dirty snowballs of dust and frozen gases that blaze as they near the sun. Yet even as science demystified them, This sense of strangeness never fully left. And now, with Threeey Atlas swelling into a plasma cloud half the size of the Sun, interacting with currents in ways we cannot predict, a different kind of speculation emerges. What if this object is not entirely natural? What if, hidden within its vast coma, lies something engineered? The suggestion that comets could conceal technology is not new. In the mid-20th century, as humanity entered the space age, scientists and writers alike wondered if alien civilizations might use natural objects as cover. An interstellar probe disguised as a comet would be almost impossible to detect among countless icy wanderers. Its trajectory would raise no suspicion. Its surface would appear inert, frozen, ordinary. Only subtle anomalies in behaviour, unexpected acceleration, unusual outgassing, strange magnetic properties might hint at something more, and those anomalies, in recent years, have begun to appear. When One-Eye Oumuamua passed through the solar system in 2017, it sparked a debate still unresolved. Its elongated shape, its lack of a visible coma, its unexplained acceleration as it left the Sun, none of these fit comfortably within existing comet or asteroid models. Some scientists proposed exotic explanations involving hydrogen ice or fractal dust. Others quietly suggested that it might be artificial, perhaps a fragment of a solar sail or a probe sent long ago. The idea gained traction not because of science fiction, but because of the limits of natural explanation. When physics struggles to account for an object's behaviour, speculation fills the gaps. Threeey Atlas invites similar speculation. Unlike Oumuamua, it carries a visible coma, vast and luminous. But its behaviour is unusual. Its plasma envelope has expanded at rates that exceed models. Its interactions with the solar wind have produced anomalies that standard forecasts cannot explain. Instead of storms fading with expected decay rates, disturbances linger, as though something within the coma sustains the turbulence. Some have proposed that this is due to the unique composition of an interstellar object, ices and materials unlike those found in the Kuiper belt. Others wonder if we are watching the signature of something else, an engineered system that uses plasma for purposes we cannot yet fathom. The idea of alien technology concealed within a cometary body might seem outlandish, but consider the advantages. Comets are natural shields. They're ice and dust capable of absorbing radiation, protecting delicate machinery within. Their tails can mask emissions, making detection by primitive instruments nearly impossible. Their trajectories bring them close to stars, where they can gather energy before flinging them back into interstellar space. For a civilization advanced enough to engineer on such scales, comets could be ideal vessels or cloaks for probes, beacons or other technologies. Humanity itself has already considered disguising future interstellar probes within asteroid shells to avoid detection or damage. The concept is not science fiction. It is engineering foresight. If Threeey Atlas was such a vessel, what might its purpose be? Speculation branches in many directions. It could be a passive probe, designed simply to observe civilizations as it passes through their systems, hidden from sight. It could be an active device, sending or receiving signals using its plasma coma as an antenna to transmit across vast distances. It could be part of a network, one of many seeded through the galaxy to monitor, to map, or to wait for civilizations to reveal themselves. Or it could be something beyond our comprehension, a technology so advanced that our categories of probe and vessel no longer apply. Skeptics rightly point out that extraordinary claims require extraordinary evidence, and so far, no such evidence exists. What we have are anomalies, curiosities, behaviours that stretch our models. But history shows that anomalies often precede breakthroughs. The strange orbit of Mercury led to general relativity. The unexpected radiation in uranium led to nuclear physics. When nature behaves oddly, it tells us something new. Whether Threeey Atlas tells us about exotic ices, unusual plasma dynamics, or alien technology remains the question. One of the most intriguing possibilities involves its interaction with the solar wind. Plasma physicists know that controlled turbulence can be used to manipulate energy flows. On Earth, experiments with fusion devices rely on managing plasma currents. If Threeey Atlas sustains turbulence longer than expected, could it be because something within is shaping the plasma deliberately? Could its coma be functioning as a vast antenna, a shield, or even a propulsion system? The scale seems impossible to us, but to a civilization millions of years ahead, it might be as trivial as shaping currents in a laboratory is to us now. This speculation gains weight when we remember how comets have been tied to human events for millennia. Every time a great comet appeared, societies changed. The fall of Rome coincided with unusual celestial phenomena. The Norman conquest was heralded by Halley's Comet. Even the Black Death in Europe came with reports of comets blazing in the skies. Historians view these as coincidences, but in a magnetic universe, comets do influence Earth through plasma interactions, storms, and turbulence. If natural comets can shape history through physics, how much more could an engineered one do? The public response to Threeey Atlas has been muted compared to Oumuamua. Few outside scientific circles are even aware of its presence, but within those circles the unease is real. Papers are cautious, language restrained, conclusions tentative. Yet between the lines the same question hovers. Why is this object behaving the way it does? Why do its interactions with the solar wind persist beyond expectations? Why do disturbances cluster around its path? In the absence of clear answers, speculation about alien technology remains one possibility among many. For humanity, the implications of such a discovery would be profound. If Threeey Atlas were natural, it teaches us about interstellar chemistry, about plasma physics, about the diversity of cosmic wanderers. If it were artificial, it would mean we are not alone, that civilizations far older and more advanced than ours have already seeded the stars with their presence. It would mean we are being observed, perhaps studied, perhaps contacted in ways too subtle for us to notice. It would mean that history has been unfolding not in isolation, but under watchful eyes. Even if the truth proves mundane, the act of asking the question changes us. To speculate about alien technology in a comet is to recognize that we live in a universe of possibilities. It is to admit that we do not yet understand the full range of what exists beyond our planet. It is to stretch our imagination to match the scale of the cosmos. And in that stretch, we prepare ourselves for discoveries yet to come. The alien technology speculation does not need to be proven to matter. It matters because it forces us to confront the unknown honestly. It matters because it prevents us from assuming that the universe is simple, predictable, or fully explained. And it matters because, in the presence of a plasma cloud half the size of the Sun, expanding and interacting in ways we cannot model, the question is not absurd. It is reasonable, even necessary to ask. The secret may never be revealed. Threeey Atlas will pass, its coma will fade, its core will drift back into interstellar space. Whether it leaves behind data that proves natural or artificial, it will have changed us by the questions it raised. For now, we watch, we measure, we speculate, and in the silence of space, in the turbulence of plasma, in the anomalies of behaviour, we listen for the possibility that we are not alone. There are moments when the line between deliberate action and natural randomness blurs so completely that we can only ask the question out loud and listen for an answer. Did something or someone reach across the void and prod the sun, the solar wind, or the crust of the earth? Or are we simply witnessing forces that, by their nature, produce patterns that mimic intention? The choice between directed energy and natural chaos is not a neat fork in the road. It is a spectrum, and in the middle lies the uncomfortable possibility that both may be true in different ways. Natural processes shaped by contingencies, or engineered interventions disguised by the very complexity they exploit. Start with what we know. Energy in space does not behave like energy in our day-to-day world. There is no air to slow things down, no friction to bleed away motion. Instead, electromagnetic forces dominate. Charged particles gyrate along magnetic field lines. Plasma, collections of ions and electrons, flows, eddies, and reconnects with a kind of furious elegance. Natural systems of plasma and magnetism can produce phenomena that look organised, even purposeful, because their internal dynamics favour certain stable structures, filaments, sheets, spirals. When a large coherent structure like the coma of Threeey Atlas enters the heliosphere, it can trigger those self-organising behaviours. The result can appear to an outside observer as if someone tuned the system to produce a desired effect. That is one face of natural chaos, the spontaneous emergence of order from complexity. Now consider the other face, directed energy, in the context people confront when they imagine technological actors on a cosmic scale, is not necessarily laser beams or weaponized microwaves. It can be the deliberate shaping of plasma, the controlled injection of current, the manipulation of magnetic fields on scales that dwarf human engineering. In laboratories on Earth, we already exploit similar principles in miniature. Confine plasma with magnetic bottles, drive currents to induce specific behaviours, manipulate fields to accelerate particles. Scale those tools up and apply them to the environment of a star, and the theoretical possibilities widen dramatically. An engineered system operating at that scale might use the comet-like body not as a projectile, but as a platform, a distributed array for harvesting solar wind energy, a gigantic antenna to reconfigure heliospheric currents, or a directed means to test the magnetic response of a planet. What makes the question so compelling now is how neatly some recent anomalies fit both narratives. Prolonged geomagnetic disturbances, low-density solar wind episodes, and seismic clusters that align in time with space weather events can be read two ways. They can be read as natural consequences of an unusual plasma object moving through the solar wind, bending fields and creating turbulence, or they can be read as the signatures of a system deliberately modulating plasma flows to achieve some objective. Neither interpretation is easily proven, both demand extraordinary evidence. But neither can be discarded out of hand when the scale of the coma and the timing of events conspire to make coincidence feel less plausible. To investigate the directed energy hypothesis, one must examine the physics of coupling between plasma structures and planetary responses. At the heart of the matter is coupling efficiency. How effectively can changes in the heliospheric environment translate into currents and forces within a planet's magnetosphere and crust? In a simple sense, coupling is achieved when moving magnetic fields induce electric fields. Changing electric fields drive currents. On Earth, these induced currents are already a known hazard to infrastructure. They flow through power lines, pipelines, and long conductive paths. If an engineered device could manipulate the interplanetary magnetic field orientation, or create sustained phase-locked fluctuations, it could, at least theoretically, shape the distribution and timing of induced currents on planetary scales. That is an engineering problem more than a magical one. It requires a platform capable of creating coherent, large-scale magnetic perturbations over days or weeks, precisely the circumstance that a massive, actively maintained plasma coma might provide. Natural chaos, however, offers plausible mechanisms that do not require intelligence. Plasma wakes, for instance, produce coherent cavities and downstream vortices when a large obstacle moves through a flow. Those wakes can sustain oscillations that persist long after the obstacle has passed. Magnetic reconnection in such environments can see turbulent cascades, generating a spectrum of fluctuations that resonate with structures in the heliosphere. Because resonances preferentially amplify particular frequencies, a natural plasma system can concentrate energy into modes that influence the magnetosphere more effectively than random noise would. In other words, the physics of plasmas naturally gives rise to selective amplification. So natural behaviour can masquerade as directed behaviour simply because the medium prefers certain responses. There are practical differences, and they point the way to tests. An engineered system, to be practical, would likely aim for predictability, control the timing of pulses, shape spectral content of perturbations, or target specific magnetic latitudes. Those signatures would be repeatable and structured in ways that nature rarely reproduces. Natural turbulence, by contrast, tends to be stochastic, broadband, intermittent, and sensitive to initial conditions. If we could find repeated patterns in the timing or spectral shape of magnetic disturbances that match no expected solar cycle behaviour, and if those patterns align with the motion of the interstellar object in a way that requires active steering, then suspicion would grow. Conversely, if the anomalies are broadband, variable and track, with models of fluid plasma interaction, when a large conductive body is introduced, then natural processes would appear sufficient. Ask the uncomfortable empirical questions. Has the interplanetary magnetic field shown signatures that match controlled modulation? Have the frequencies of induced geomagnetic oscillations displayed regularity beyond natural resonance? Do seismic events correspond tightly, not just to disturbances, but to particular phase patterns of electromagnetic flux that would suggest timing and purpose? So far, the observational record suggests complexity rather than simple control. Storms linger, vacuums whisper, and quakes cluster. Facts that warrant skepticism but do not single out deliberate engineering. Yet the richness of the anomalies also means that ruling out directed effects altogether would be premature. Another consideration is motive and capability. On a cosmic scale, technological actors, if they exist, operate on timelines and with energy budgets far removed from human concerns. What possible motive would justify the expenditure of resources required to shape space weather around another star? Scientific curiosity, perhaps, or the desire to probe planetary responses for the sake of future interactions? Understanding how a planet's magnetosphere and geology react to external electromagnetic forcing could reveal much about its habitability and internal structure. Alternatively, more strategic motives could be imagined. A probe testing resilience, a system harvesting energy where planetary magnetic fields enhance collection efficiency, or even a survey mission covertly probing for biosignatures by observing planetary responses to controlled stimuli. Capability is the harder prerequisite. Engineering on the scale of a star's heliosphere requires materials, control systems, and energy sources that dwarf our current experience. But consider that an interstellar object can serve as leverage. A modest nucleus enveloped by a vast coma acts as a medium to interact with the solar wind without needing to displace unimaginably massive objects. If you can control how ionization unfolds across a coma, pump energy into certain species, catalyze ionization in phases, or deploy structures that preferentially align with magnetic fields, you can influence the flow indirectly. It is not the scale of the core that matters as much as the scale of the interaction in the envelope. A small seed can produce a huge footprint if the physics are harnessed intelligently. Yet even the directed energy hypothesis faces practical obstacles. Planetary scale effects are messy. To do anything that consistently nudges tectonic systems would require an intimate understanding of crustal stress states and coupling factors that we ourselves do not yet fully map. The timing windows for influencing quake timing, for instance, are narrow. Faults load and unload over years or centuries. To advance the timing of a rupture by days or hours would require precise knowledge of failure thresholds and a means to deliver exactly the right perturbation at the right location. That is not impossible for an advanced system, but it is non-trivial. It would argue for long-term observation and patient experimentation rather than hasty destructive interventions. Where this conversation becomes most dangerous is in how it shapes public perception. Suggesting deliberate manipulation of natural systems, whether by alien intelligence or hypothetical human technology, tends to slide into melodrama and fear. Alarmism thrives on uncertainty. Yet scientific inquiry must not be chilled by the politicization of speculation. The ethical approach is to pursue data, to test hypotheses with openness and rigour, and to distinguish between what is probable, what is possible, and what is purely speculative. Directed energy is possible in principle, but possibility is not a substitute for evidence. So how do we proceed experimentally? The tools lie within our reach in principle. Multi-point observations across the heliosphere, combining in situ plasma measurements with ground-based magnetometers and dense seismic networks, can detect phase relationships and spectral content of disturbances with increasing fidelity. If anomalies tied to the comet's motion show structured, repeated signatures, spectral lines, phase coherence, or beam-like propagation, then the directed hypothesis gains plausibility. If disturbances remain broadband, transient, and explainable by magnetohydrodynamic models, then natural explanations hold stronger sway. The key is not to choose a narrative in advance, but to let data accumulate and patterns emerge. There is an uncomfortable humility in all of this. Human science is a method for pruning plausible stories into reliable knowledge. At the edge of cosmic phenomena, the pruning takes time. The arrival of Threeey Atlas gives us a natural experiment we did not schedule. For months, the heliosphere will be perturbed, the magnetosphere tested, the crust nudged, and our instruments will record the results. The patterns will be messy. Some will be explainable within existing frameworks, others will demand new theory. In the best-case scenario, we will learn new plasma physics, improve resilience of our technology, and refine geological models. In the worst-case scenario, we will have convinced ourselves of intentions where none exist. If, however, evidence begins to appear that cannot be reconciled with natural processes, if coherent modulation, repeatable control, or artifacts of design are observed, then the implications change abruptly. We would confront not just a scientific puzzle, but a profound historical moment. The discovery of a deliberate actuator within our heliosphere would force a re-evaluation of assumptions about agency in the cosmos. The ethical questions would be unavoidable. What rights does a technological artifact have? What obligations do we have to respond? How do we interpret its motives? Until then, the responsible posture is to hold both possibilities in mind. Natural chaos capable of producing quasi-organized effects, and directed systems that could, under certain plausible architectures, produce them as well. We watch the data, test models, and refuse to let fear dictate conclusion. The comet moves through the sun's breath like an oar through a river. Eddies form and patterns emerge. Whether those patterns are the product of a hand guiding the oar or the physics of flow itself is the question that the coming months of observation will answer. For now, live with the ambiguity. It forces clarity in how we gather evidence, how we model phenomena, and how we talk about risk. It reminds us that extraordinary claims require rigorous tests, and that the universe, whether engineered or natural, often exceeds our intuitions. In the end, the most valuable outcome is not to settle on a sensational narrative, but to deepen our understanding, so that whatever the origin of the disturbances, we're better prepared, more resilient, and more curious about the depths of physics and possibility that surround us. Above our heads, unseen and mostly unacknowledged, a vast shield stretches out into space. It is not a wall of stone or metal, but a field of invisible force, born from the restless movement of molten iron in Earth's core. This magnetic shield, the magnetosphere, is our planet's first line of defense against the solar wind, the endless stream of charged particles thrown outward by the sun. Without it, Earth would resemble Mars, its atmosphere stripped away long ago, its surface blasted by radiation, its oceans long since evaporated into space. With it, life has endured, shielded for billions of years from the full fury of the cosmos. But even shields can weaken, bend, or fail. and today this one is under pressures greater than at any time in human memory. The magnetosphere is not static. It shifts and flexes with the solar wind, compressing on the day side, stretching into a long tail on the night side. It vibrates, ripples, and occasionally cracks when magnetic reconnection tears open portals that allow energy and particles to pour in. Under normal conditions, it is resilient, able to absorb solar gusts and recover quickly. But when conditions change, when storms intensify, when plasma clouds expand, when the solar wind carries prolonged turbulence, the shield comes under sustained pressure. That pressure is not merely academic, it translates into real effects: geomagnetic storms, auroras, power surges, communication failures, and more subtly, shifts in Earth's own rhythms. Earth's magnetic field is already in a weakened state. Over the past century, measurements have shown a steady decline in field strength, with regions like the South Atlantic anomaly growing increasingly vulnerable. In that zone, satellites regularly experience glitches as radiation penetrates more easily. Scientists interpret this as part of a long cycle, the slow wandering of the magnetic poles, which sometimes culminates in a reversal where north becomes south and south becomes north. These reversals have occurred many times in Earth's history, often accompanied by periods of instability lasting thousands of years. We may be in the midst of such an interval now, with the shield not collapsing entirely but fluctuating in ways that leave Earth more exposed. Add to this natural vulnerability the growing intensity of solar activity. The sun is climbing toward maximum, unleashing flares and coronal mass ejections at increasing rates. High-speed solar streams carve into the heliosphere, colliding with slower winds and creating turbulent fronts. Each time one of these fronts reaches Earth, the magnetosphere is battered, forced to contract to half its usual size, exposing satellites in higher orbits and flooding near-Earth space with energetic particles. In the past, the storm came and went, disruptive but manageable. But with the presence of Threeey Atlas, the turbulence lingers, storms stretch longer, vacuums create strange expansions, and the shield is left in a constant state of strain. This strain is not always visible to the public. To most people, the magnetosphere is invisible, intangible, not part of daily thought. But its weakening reveals itself indirectly. Auroras appear in skies far from the poles, lighting cities unaccustomed to their glow. GPS signals drift, sometimes by meters, disrupting navigation. Airlines reroute flights away from polar routes during radiation surges. Satellites fall from orbit faster than expected as the upper atmosphere heats and swells. These are the signs of a shield under pressure, signs that life at the surface only notices in inconveniences, but that specialists see as warnings. The shield is also critical to climate stability. By deflecting cosmic rays, it influences cloud formation and atmospheric chemistry. A weakened field allows more high-energy particles to penetrate, increasing ionization in the upper atmosphere. Some studies suggest correlations between cosmic ray flux and patterns of cloudiness, though the mechanisms remain debated. If the shield weakens further, climate itself may be subtly nudged, not through greenhouse gases or volcanic eruptions, but through invisible rain from the galaxy itself. In this way, Earth's magnetic field connects the deep interior of the planet to the vast structures of interstellar space, tying geology, atmosphere, and life into one fragile balance. Consider too the psychological impact of living in an era when the shield shows strain. Ancient people may not have known the physics, but they noticed the signs: strange lights in the sky, compasses wandering, animals behaving oddly before earthquakes or storms. Today, we experience similar anomalies, but with instruments that quantify rather than interpret. Yet the effect is the same. There is unease in knowing that the planet's primary defense is fluctuating. There is unease in watching auroras where they should not be, in hearing reports of satellites glitching, in knowing that a visitor from another star is stirring currents that add to the strain. Humanity, like the ancients, senses vulnerability when the sky itself begins to act strangely. The shield does not fail catastrophically. It is resilient, flexible, capable of bending without breaking. But history shows that prolonged pressure can create cascading consequences. The Carrington event of 1859 was a moment when the shield was overwhelmed, when telegraph lines sparked and auroras glowed over the tropics. If such an event occurred today, with modern infrastructure dependent on electricity and satellites, the damage would be immense, trillions of dollars, weeks or months of recovery. Engineers work to harden systems, but the vulnerability remains. And now, with turbulence from an interstellar coma adding to the stress of solar maximum, the probability of such an event rises, not as certainty but as possibility worth preparing for. Some researchers propose that the shield itself may be adaptive, that its fluctuations are not simply weaknesses but part of its resilience. By reconnecting and vibrating, by oscillating under pressure, it dissipates energy rather than shattering. In this sense, Earth's magnetic field acts like a living system, responding dynamically to changes in its environment. Yet this adaptability has limits. If the turbulence is too prolonged, if the weakening too deep, the shield's ability to rebound may falter. What happens then is not extinction. Life has endured reversals before, but disruption on scales that challenge human civilization. The presence of Threeey Atlas makes this moment unique. Never before in human history has a plasma cloud of such scale entered the heliosphere during a period of magnetic weakening and solar maximum. We are witnessing an unrepeatable experiment, one that no laboratory could create, one that unfolds in real time across the planet. Every aurora, every power surge, every seismic tremor becomes a data point in this experiment. The shield is under pressure, and we are watching how it responds. Perhaps what matters most is perspective. The magnetic field has endured billions of years, weathering reversals, solar storms, and cosmic intrusions. It may endure this as well. But for humanity, dependent on fragile technologies and global networks, the margin of safety is narrower than ever. We live within a shield that we cannot repair, a shield that we can only observe and adapt to. And as it bends under pressure from the sun, from turbulence, from an interstellar visitor, we are reminded that our world is not separate from the cosmos. It is part of it, vulnerable to its rhythms, protected only as long as the shield holds. The story of Earth's magnetic shield under pressure is not one of imminent collapse, but of awareness. It is the recognition that what protects us is dynamic, fragile and responsive to forces we cannot control. It is the recognition that our resilience depends not only on geology or atmosphere, but on magnetism, an invisible field born in the depths of the Earth and stretched across space. And it is the recognition that as this shield comes under greater pressure, we too are being tested, not just in our science, but in our preparedness, our imagination, and our ability to live with the knowledge that the universe presses in on us more strongly than ever before. For most of history, comets were seen as passive wanderers. They were omens in the night sky, not agents in the unfolding of events. Science refined that view, describing them as frozen leftovers from planetary formation, icy bodies that flared when warmed by the sun. Yet that description misses something vital. Comets are not passive. They are active participants in the electromagnetic web of the solar system. Their comas are conductive, their tails are currents, and their interactions with the solar wind are dynamic. When the conditions align, comets do not merely glow, they amplify. They take existing energy flows and increase their intensity, becoming nodes that broadcast turbulence across astronomical distances. And now with Threeey Atlas, we are watching amplification on a scale never before seen. The principle is simple. Plasma is a medium of amplification. When charged particles stream past a conductive body, fields are induced, currents are generated. Those currents can resonate with the larger system, producing oscillations that extend beyond the body itself. On Earth, this principle is used in antennas. A small conductor resonates with radio waves, amplifying them enough to be detected. In space, comets act as enormous antennas. Their comas, stretching hundreds of thousands of kilometers, become resonant structures that interact with the solar wind. When they align with currents flowing outward from the sun, they amplify them, sending disturbances downstream. This is not speculation. Observations of smaller comets within our own system show that their plasma tails connect to the sun through magnetic field lines. During solar storms, these tails can break, reconfigure, or glow more brightly as energy surges through them. Some comets have even been observed producing their own magnetic fields temporarily, acting like miniature planets within the solar wind. If small comets can do this, what happens when the coma expands to half the size of the sun? The amplification potential is immense, a cosmic-scale antenna embedded in the very circuits of the heliosphere. For Earth, the consequences are subtle but measurable. The storms we're experiencing now do not behave like past storms. They persist longer, fluctuate oddly, and create anomalies in power grids and satellites that defy existing models. It is as if the energy of the solar wind is being recycled, its turbulence sustained instead of dissipating. Amplification explains this. Threeey Atlas, with its massive coma, absorbs solar particles, resonates with their flows, and re-emits turbulence into the system. The result is storms that should have ended but continue, disturbances that should have faded but linger. Earth sits downstream of this amplification, caught in a resonance we do not yet fully understand. Amplification also explains the strange clustering of geomagnetic and seismic events. A solar storm by itself may trigger minor disturbances, but if that storm is amplified by a cometary node, its effects can double, triple, or extend in duration. Fault lines near rupture may respond to that added push, producing swarms of quakes. Power grids designed to handle short surges may falter under prolonged oscillations. Satellites hardened for bursts may degrade under continuous bombardment. Amplification transforms ordinary storms into extraordinary ones, not by creating new energy, but by redirecting and magnifying what already exists. The metaphor of a musical instrument is helpful. A violin string plucked in silence produces a faint sound. Pressed against the body of the violin, it resonates, amplifying into music that fills a room. The string did not create more energy, it simply transferred it more efficiently. Comets act in a similar way, their comas becoming resonant bodies that amplify the solar wind's vibrations. And when that body is the size of a star's corona, the music can be heard across the system. Earth, whether ready or not, is listening to the notes now. Historically, comets have coincided with upheaval. Wars, plagues, and disasters were blamed on their appearance. Historians dismiss this as superstition, but perhaps the ancients were noticing amplification effects without knowing it. A comet arrives, the sky glows, the weather shifts, earthquakes cluster, societies falter. These patterns, repeated across centuries, may not be purely psychological. They may be the signatures of comets amplifying cosmic currents, altering the environment in ways that ripple into human history. Threeey Atlas is unique because it is interstellar. Its composition is unfamiliar, its stability unknown, its behaviour unprecedented. It may contain ices and materials that ionize differently, sustaining its coma longer than expected. Its plasma interactions may be stronger, its resonance sharper. If so, the amplification we are seeing now may be only the beginning. As it moves closer to the sun, its coma will expand further, its currents will strengthen, and its role as an amplifier will grow. By autumn, when planetary alignments concentrate flows and solar activity peaks, the amplification could be unlike anything in recorded history. There is a darker possibility. Amplifiers can become unstable. In electronics, feedback loops create oscillations that spiral out of control, producing noise instead of signal. In nature, resonance can collapse systems. Bridges shatter under rhythmic stress. Buildings fall under harmonic vibrations. If Threeey Atlas amplifies currents beyond the ability of the heliosphere to absorb, the result could be a cascade of turbulence, storms feeding storms, anomalies compounding into chaos. Earth would not be destroyed, but its systems would be strained, its resilience tested in ways we have not imagined. This is not to say catastrophe is certain. Amplification can also reveal patterns, making visible what was once hidden. Just as a microphone amplifies whispers, comets amplify cosmic currents, exposing structures we might otherwise overlook. The turbulence downstream of Threeey Atlas may teach us more about plasma physics than decades of controlled experiments. By studying the amplification, we may uncover resonances that shape not only our solar system, but the galaxy at large. In this sense, the comet is both a threat and an opportunity, both a destabilizer and a teacher. The practical response is preparation. Power grids must be monitored more closely, satellites shielded more carefully, flight paths adjusted more flexibly. Scientists must expand models to include amplification, not just direct solar input, and humanity must accept that comets are not passive wanderers, but active participants in a cosmic circuit. The myth of comets as omens may be truer than we realised, not as supernatural warnings, but as natural amplifiers of forces that ripple into human lives. The secret of amplification is that it does not require intention. It is a natural consequence of physics. Yet the possibility remains that intention could be involved. An advanced civilization, understanding plasma physics better than we do, might exploit comets deliberately as amplifiers, seeding systems with probes disguised as comets, using their comas as antennas, shaping currents to study or influence planets. If Threeey Atlas is natural, it teaches us about plasma. If it is engineered, it teaches us about others who already know. Either way it teaches, and either way we must learn. The comet continues to expand. Its coma grows larger, its amplification stronger, its influence broader. Earth remains downstream, feeling the turbulence, watching auroras glow, recording anomalies in data and in daily life. Whether natural or intentional, the amplification is real, and as the weeks pass we will see more of its consequences, some disruptive, some enlightening, all reminders that in a magnetic universe, nothing is truly isolated. Everything resonates, and comets are the amplifiers of the song. October has always been a month when the sky feels closer. In the northern hemisphere, the nights lengthen, the air cools, and the stars seem sharper, as if the thinning atmosphere brings the cosmos within reach. Historically, it has been a season of omens, harvest moons, and celestial alignments that marked the change of the year. This October, however, carries more than seasonal symbolism. It marks a convergence, a nexus of timing in which planetary alignments, solar maximum, and the lingering presence of Threeey Atlas all intersect. The October nexus is not simply a date on a calendar. It is a window when multiple factors align to place Earth in a position of heightened vulnerability and heightened awareness. A cosmic experiment unfolding before our eyes. The setup has been building for months. The sun's activity has increased steadily, producing flares and coronal mass ejections at a pace not seen in over a decade. Geomagnetic storms have become routine, battering Earth's shield, producing auroras at latitudes where none should appear. At the same time, the interstellar visitor, Threeey Atlas, has expanded its coma into a plasma structure so vast that it reshapes the flow of the solar wind. Disturbances that should dissipate linger instead. Vacuums appear in data, intervals when the solar wind thins to a whisper before surging again as though energy is being absorbed and released. Meanwhile, planetary orbits are bringing alignments that concentrate gravitational and magnetic influences into narrow arcs. Each of these factors alone would be notable. Together, they form the nexus. October has a special place in space weather history. The Carrington event of 1859, the most powerful geomagnetic storm on record, occurred in early September, but was followed by months of continued disturbances into October. The Quebec blackout of 1989 was triggered in March, but the months that followed, including October of that year, showed prolonged solar turbulence. More recently, several severe storms in 2003, known as the Halloween storms, struck in late October, disrupting satellites, damaging transformers, and dazzling skies with auroras visible deep into southern latitudes. October, in other words, has precedent. It is a month when solar activity and geomagnetic response often reach climaxes. This October differs because of the added factor of Threeey Atlas. For the first time, an interstellar object with a coma larger than the Sun will be present during solar maximum, during planetary alignments, during the seasonal period when Earth's tilt exposes it more directly to solar-wind interactions. The nexus is a stacking of conditions, not a single event, but a window when probabilities rise, when patterns converge, when the normal becomes amplified. Scientists who track space weather do not speak of certainty. They speak of likelihoods, and this October, the likelihood of unusual phenomena is higher than at any time in recent memory. What might this mean? The most visible signs will likely be auroras. Already they have descended into regions unaccustomed to their light. In October, skies over Europe, North America and Asia may glow more often, more vividly, more unpredictably. For some, this will be a spectacle, a reminder of the beauty of the cosmos. For others, it will be a warning, a sign that the shield above is under pressure. Less visible will be the effects on technology, satellites encountering radiation storms, GPS signals deviating, communications faltering, power grids straining under induced currents. These effects may not be catastrophic, but they will be disruptive, especially in systems stretched thin by global dependence. There is also the question of seismic parallels. In recent years, patterns have suggested that solar storms and low-density wind events correlate with swarms of earthquakes. The mechanism remains debated, but the coincidence grows harder to dismiss. October's nexus may bring further test of this correlation. If storms amplify, if currents linger, if fault lines already under stress receive subtle nudges, then tremors may cluster again, perhaps in regions where seismic risk has been underestimated. It would not be the first time. The Indian Ocean quake of 2004, the Chilean quake of 2010, the Japanese quake of 2011, all coincided with unusual solar activity. If October brings similar activity, the parallels will sharpen once more. Beyond physical consequences lies the psychological weight. A nexus is not only a stacking of forces, but a stacking of perceptions. People notice patterns, they connect dots. When auroras appear, when earthquakes strike, when headlines speak of interstellar visitors, the sense of unease grows. Ancient cultures translated that unease into stories of gods and omens. Today, we translate it into speculation about plasma physics, directed energy, and cosmic coincidences. The form changes, but the feeling does not. October will be a month when the sense of cosmic connection is heightened, when people feel that the sky's pressing closer, that the Earth is responding to forces beyond its control. It is important to recognize that not all of this is danger. A nexus can also be an opportunity. The convergence of conditions creates a natural laboratory, one that scientists could never build but can now observe. Instruments on Earth and in orbit will record data of unprecedented richness. Every aurora, every storm, every anomaly will carry information about plasma physics, about solar wind dynamics, about the interaction between interstellar matter and the heliosphere. If humanity can resist the temptation to leap to fear, it can harvest understanding. The October nexus may destabilize, but it will also reveal. Yet even with this optimism, the uncertainties remain. Turbulence amplified by Threeey Atlas may not follow familiar patterns. Feedback loops may create storms that linger far longer than models predict. Currents may resonate with Earth in unexpected ways. Planetary alignments may sharpen instabilities rather than disperse them. The nexus is not a controlled experiment, it is an uncontrolled one. Humanity is not the experimenter but the subject, caught in a system whose variables are too large to manipulate and too complex to predict. That is what gives October its weight, not certainty of catastrophe, but certainty of unpredictability. As the month approaches, preparations quietly intensify. Agencies that monitor space weather issue cautious advisories. Grid operators review protocols for induced currents. Airlines adjust contingency plans for rerouting. Seismologists compare notes with solar physicists, curious but cautious. None of this makes headlines. The public is not told to fear October, but within specialist circles there is awareness that the coming weeks may test assumptions, may stress systems, may reveal vulnerabilities hidden in plain sight. Looking further, one might ask whether this nexus is part of a larger rhythm. Are there cycles when interstellar intruders, solar maximums and planetary alignments coincide? Or is this a singular event, a chance alignment that may not repeat for millennia? The data is too sparse to know. We have only 2 interstellar visitors on record before this, neither with such a vast coma. We have centuries of solar cycles, but only in the past few decades have we observed them in detail. We have millennia of earthquake records, but only in the past century have we correlated them with solar and magnetic data. The October nexus may be a unique moment in human observation, one that defines how we think about such convergences in the future. For individuals, the experience will vary. Some will look up at skies alive with auroras and feel awe. Some will watch news of storms and quakes and feel fear. Some will scroll past headlines about plasma comas and never think twice. But beneath all of this, the reality will be the same. The Earth is entering a period when multiple cosmic forces overlap, when its shield is tested, when its systems are nudged, when its people are reminded that they are not separate from the universe, but immersed within it. The October nexus approaches, not as prophecy, but as convergence. It is not a single event, but a season. Not a catastrophe, but a test. Not a message, but a pattern. And as it unfolds, it will show us more clearly than ever how the magnetic universe connects sky and ground, how an interstellar visitor can shape daily life, how history itself is written not only by human actions, but by cosmic rhythms. The nexus is coming. What it reveals depends not only on the forces at play, but on our ability to notice, to prepare, and to understand that sometimes the most important changes do not come with thunderclaps, but with convergences, with currents, with a season when everything seems to align. Humanity has always been both participant and observer in the grand theatre of the cosmos. For most of our history, we lack the tools to measure, so we watched with naked eyes and filled the gaps with stories. We called the comets harbingers, we read alignments as omens, we saw auroras as gods in the sky. The narratives changed as our instruments improved, but the role did not. We are still watching, still trying to make sense of patterns that dwarf us. The difference now is that the experiment is visible in ways the ancients could not imagine. A laboratory stretching from the sun to an interstellar visitor, with Earth placed right in the middle of it. Humanity is both subject and spectator, caught in a test it did not design, yet determined to learn from it. The experiment begins with the sun, as it always does. Its cycles of activity are not under our control, but they are increasingly under our gaze. Satellites measure the brightness of flares, the density of the solar wind, the orientation of magnetic fields. Probes stationed at Lagrange points act as sentinels, giving us hours of warning before storms arrive. Earth-orbiting spacecraft monitor the auroras, the ionosphere and the crustal responses. Ground-based magnetometers hum with real-time data. recording oscillations invisible to the eye but obvious to instruments. Together, these tools allow us to see the invisible shield that protects us, and more importantly, to see when that shield is pressed beyond comfort. Into this system enters Threeey Atlas, the uninvited participant. Its coma expands, its plasma tail connects to the sun, and its sheer scale ensures that the normal order of the heliosphere is perturbed. We cannot switch it off, cannot remove it, cannot predict it with confidence. But we can watch. We can chart how storms change in its presence, how anomalies cluster, how the Earth responds differently than expected. Each data point becomes part of a case study, each anomaly a clue. Scientists across disciplines, plasma physics, seismology, atmospheric science, find themselves watching the same object, interpreting its influence through their own lenses. In this way, the comet is not only an amplifier, but a unifier, forcing once isolated fields to compare notes and confront the possibility of deeper connections. Humanity watches not just with instruments, but with imagination. For some, the comet is a natural laboratory, a chance to refine models of plasma turbulence, to test theories of solar-terrestrial interactions, to prepare for future interstellar encounters. For others, it is a possible artifact, a vessel, a probe, a reminder that the universe may contain intelligence older and more capable than ours. The scientific papers are careful, the language measured, but the public speculation fills the gaps. Every unexplained disturbance becomes a potential signal, every anomaly a possible intention. In the quiet hours of the night, when auroras glow and headlines speak of storms, the line between physics and wonder blurs. Watching the cosmic experiment is as much about grappling with possibility as it is about collecting data. The experiment is not limited to space. Earth itself is part of it, its crust responding to currents, its atmosphere shifting under ionization, its technologies straining under induced surges. Each tremor, each blackout, each deviation in climate patterns becomes a data point. To seismologists, quakes are tectonic releases. To atmospheric scientists, weather is circulation. To electrical engineers, blackouts are technical failures. Yet when those events cluster around geomagnetic storms and cometary turbulence, the broader view emerges. Earth is being tested as a whole system, its geology, atmosphere, magnetosphere, and civilization all responding in concert to pressures from above. History provides perspective here. The Carrington event was not understood in its time. It was curiosity, a strange storm that set telegraphs on fire. Today, we look back and see it as a data point, a natural experiment in extreme solar forcing. The Quebec blackout of 1989 is another, more recent, more measurable. Each event is both a disruption and a lesson. Now, with Threeey Atlas, we may be experiencing the next in that sequence, a prolonged natural experiment that future generations will analyse as we now analyse Carrington and Quebec. Humanity watches because it knows that history is not only written in books but in data, in storms, in events that reshape understanding. The cosmic experiment is not controlled. Variables overlap, turbulence resists neat boundaries, and causation hides within layers of coincidence. That is what makes it both frustrating and valuable. A laboratory on Earth isolates variables. Space refuses to cooperate. But in that refusal lies truth. If we want to understand how systems interact on planetary and cosmic scales, we must study them when they interact freely without our design. That is what Threeey Atlas provides. A situation too large for manipulation, too complex for control, too real to ignore. The experiment runs whether we like it or not. Our role is to observe, record, interpret and adapt. There is also humility in this watching. We often imagine ourselves as masters of technology, engineers of our environment, controllers of outcomes. But faced with an interstellar plasma cloud, with a star that flares without our consent, with a shield that bends under pressure, we are reminded that mastery is partial. We are not outside the system. We are inside it, vulnerable to it, dependent on it. Watching the cosmic experiment is not just scientific, it is existential. It reminds us of our scale, our fragility, and our reliance on forces we cannot command. At the same time, watching empowers. Each new dataset strengthens our ability to predict, to adapt, to mitigate. Space weather forecasting, once rudimentary, now warns of storms hours in advance. Seismic studies, once local, now consider global triggers. Power grids, once blind, now monitor induced currents in real time. The act of watching has practical consequences, reducing vulnerability, increasing resilience. The cosmic experiment may be uninvited, but the knowledge it yields can be used, can be applied, can be turned into foresight that reduces risk. As October approaches, the act of watching becomes more intense. Observatories prepare campaigns, satellites adjust observation modes, data centers expand processing. The comet's presence ensures that anomalies will be plentiful, storms unpredictable, turbulence rich with information. Humanity watches because this is a rare opportunity, one that may not repeat for centuries. The instruments we have now, the global networks, the computational models, none of these existed during past interstellar visits. For the first time, we can truly watch in detail, not with myths or isolated observations, but with coordinated global awareness. The cosmic experiment is vast, but our gaze is sharper than ever. There remains the question of what we will conclude. Will the data confirm that comets are natural amplifiers, nodes in a magnetic universe that resonate with solar currents? Will it hint at something more deliberate, something that pushes speculation toward technology, toward agency, toward the realization that we may not be the only watchers in the cosmos? Or will it reveal only that our models were incomplete, that plasma turbulence and resonance hold more surprises than we imagined? Whatever the outcome, watching is the only way to find out. Speculation without observation drifts into myth. Observation grounds speculation in reality. Humanity watches the cosmic experiment not only with instruments but with meaning. We are meaning-making beings. We look at the sky and ask not just how, but why. The comet becomes a mirror, reflecting our fears, our hopes, our desire to connect to something larger. The cosmic experiment, whether natural or intentional, whether chaos or design, is also an experiment in our imagination. Can we live with ambiguity? Can we accept that some questions take decades, even centuries to answer? Can we find awe in not knowing, even as we seek to know? The comet will pass. The sun will continue its cycles. Earth's shield will bend and rebound. But the memory of this period will linger, encoded in data archives, in scientific papers, in cultural memory. Humanity will remember that it once watched an interstellar visitor expand to the size of the sun, once lived through storms that did not behave, once wondered aloud if it was part of something larger. Watching is not passive. It is the first step toward understanding, the first step toward resilience, the first step toward whatever comes next. The cosmic experiment unfolds, and humanity watches, not as gods watching from above, but as creatures of the earth, fragile yet aware, vulnerable yet curious. That curiosity is what defines us. It is what ensures that even when storms rage and shields bend, we keep looking upward, we keep listening, we keep asking. And in the asking, in the watching, in the patient recording of turbulence and tremors, we become part of the experiment ourselves, observers and participants at once, watching the universe as it watches us back. The longer we watch, the harder it becomes to ignore the patterns. Earthquakes cluster during storms. Auroras appear far from their normal latitudes. Power grids groan under prolonged currents. A comet from another star expands into a plasma structure large enough to rival the Sun, altering solar wind in ways that ripple through every layer of Earth's environment. Each event can be explained individually. Tectonic plates move, the Sun flares, comets outgas. But together, overlapping in time, reinforcing each other in space, they form a tapestry that feels too deliberate to be dismissed. And so, we arrive at the final question, one that has haunted humanity since the first time a streak of light crossed the night sky. Is this all coincidence, or is there design at work? Coincidence is the comfort of probability. In a system as complex as Earth, with thousands of quakes each year, hundreds of solar storms each cycle, and countless fluctuations in plasma, it is inevitable that some will overlap. Statistically, clustering happens. The mind seeks patterns, and in randomness, patterns will always appear. To say that it is all coincidence is to rest in the arms of probability, to assume that given enough events some will align in ways that seem meaningful even when they are not. Science often leans on this explanation, reminding us of the danger of apophenia, of mistaking noise for signal. The reassurance is that the universe is not conspiring. It is simply unfolding according to laws we already understand, even if we lack the computational power to model every detail. But design whispers louder than coincidence when anomalies pile up. The low-density solar winds that last longer than expected, the vacuums in data that appear too clean, the way storms linger instead of fading. These are not simply overlaps, but departures from models. When natural behaviour repeatedly defies natural expectation, the possibility of design must be entertained. Not necessarily the design of a willful intelligence in the way humans imagine, but design in the sense of underlying order, of processes structured by laws we have not yet uncovered. Or perhaps, in the most daring speculation, design in the sense of deliberate shaping by an intelligence far beyond our own. The question is sharpened by the scale of Threeey Atlas. Natural comets do not expand comas half the size of the Sun. Natural turbulence does not always sustain itself with such persistence. Natural alignments do not often cluster with such precision around seasons of heightened vulnerability. Each of these might be a coincidence. Together, they strain the definition. If coincidence is randomness, then we are forced to admit that randomness has produced an outcome indistinguishable from intention. And if that is the case, does the distinction even matter? One way to explore the question is through analogy. Imagine standing on a beach watching waves crash against rocks. Most are chaotic, splashing randomly. But every so often, a set arrives in rhythm, larger than the rest, shaped by distant storms across the ocean. Was that set coincidence? Or was it the design of physics, the resonance of waves travelling thousands of kilometres in synchrony? To the observer, the effect feels purposeful. The reality is both. Random waves punctuated by structure. The universe may be no different. Most events are noise. Some are coincidence. But within them, structure emerges. Design written not by intention but by resonance. And yet, the suspicion of intelligence lingers. We know that intelligence exists in the universe, at least here on Earth. We know that intelligence can manipulate energy, shape environments, and design systems to produce outcomes. To imagine that older, more advanced intelligences might do the same on cosmic scales is not fantasy. It is projection from what we already do in miniature. We shape plasma in laboratories. We design antennas that amplify signals. We disguise probes to avoid detection. If we can do this on small scales, why could others not do it on scales that dwarf our imagination? If Threeey Atlas were engineered, it would be operating by the same principles we understand, just expanded to a degree that feels impossible until it is demonstrated. Coincidence or design is not a binary question. It is a continuum. On one end lies pure randomness, a universe indifferent to meaning. On the other lies deliberate intention, a universe filled with agency. Between them lies self-organization, resonance, emergence, patterns that arise naturally but appear purposeful. The truth may be that what we are witnessing is all three at once. Coincidence produces overlap. Design, whether natural or artificial, produces structure. Our interpretation produces meaning. The October nexus, the storms, the quakes, the comet, all of it may be coincidence and design, chaos and order at once. For humanity, the choice of interpretation matters. If we choose coincidence, we continue with caution but without fear, treating the anomalies as opportunities to refine models, to build resilience, to understand plasma physics better. If we choose design, we open the door to questions about agency, about whether someone or something beyond Earth is experimenting, observing, or communicating through cosmic currents. That choice is not only scientific but cultural. It shapes how we think about our place in the universe, whether as isolated actors in a random cosmos, or as participants in a larger dialogue. The danger is certainty. To declare it all coincidence is to risk missing deeper connections. To declare it all design is to risk projecting intention where none exists. The safer path, and perhaps the wiser one, is to live in the tension, to accept ambiguity, to explore both possibilities without needing closure. The universe may not grant us clear answers, but it grants us the chance to ask, to measure, to imagine. That chance is the gift, the design if one chooses to see it that way. History suggests that moments like this, when humanity confronts the unknown, reshape us. The discovery of heliocentrism shifted us from the center of creation to a planet orbiting a star. The discovery of relativity shifted us from a fixed universe to one of space-time and curvature. The discovery of DNA shifted us from divine mysteries to biochemical codes. Each time, the universe revealed design where coincidence was once assumed. Each time, what seemed random was shown to follow deeper patterns. Perhaps the same will be true now. Perhaps the anomalies of Threeey Atlas, of storms and quakes and auroras, will one day be explained by laws we have not yet articulated, design hidden within physics waiting to be uncovered. Or perhaps the explanation will go further. Perhaps one day, long after Threeey Atlas has passed, signals will be detected in its wake, artifacts discovered in its trail, evidence gathered that it was not just a comet but a probe, a messenger, a device seeded by intelligence older than humanity itself. In that case, the question of coincidence or design will collapse into certainty. The universe will have answered, not with ambiguity but with revelation. Until then, we live in the in-between, where the question itself matters more than the answer. As we close this journey, what remains is perspective. The Earth is small, the Sun vast, the cosmos unimaginable. Yet within this immensity we notice, we connect dots, we wonder. That act of wondering is itself a kind of design. The design of minds shaped by evolution to seek meaning, to look for order, to refuse randomness as the final word. Whether the universe is coincidental or intentional, we are designed to ask. And in asking, we participate in the very patterns we study. Coincidence or design? The answer may not come in our lifetimes. But the act of wrestling with the question is its own reward. It sharpens our science, expands our imagination, humbles our assumptions, and reminds us that the line between chaos and order is thinner than we think. The comet will fade, the storms will pass, the shield will rebound. What remains is the memory that once, in our time, the sky grew strange, the currents amplified, the patterns overlapped, and we asked aloud whether we were witnessing chance or intention. That memory will echo, as data, as myth, as speculation, as warning, as wonder. And perhaps in that echo lies the real design. Not in the comet, not in the currents, not in the storms, but in us. In our insistence on watching, on questioning, on refusing to settle for coincidence when design might be hiding in plain sight. The final question does not close the story. It opens it into futures where answers may come, into worlds where curiosity endures, into a universe where the line between randomness and intention is the very line we are destined to walk.